In this video, I'm going to go over all of problem solving and data analysis, which is about 13.27% of the math section of the SAT. And this includes all of these subtopics as well. I hope that by the end of this video, there won't be a single one of these types of questions that you won't know how to solve. Let's get into it. First up, one variable data questions. And when I say one variable data questions, I mean any question that has something to do with mean, median, minimum, maximum, range, or standard deviation. If you see one of these words in the question, it's a one variable data question. Also, if you see one of these figures in the question, it's a one variable data question. And I'll talk more about these figures later on, but for example, if I see a box plot, you don't have to know what box plot is yet, but if you see a box plot, it's a one variable data question. Same thing if I see a frequency table. I know it's a one variable data question automatically. Let's first go over mean. And to go over mean, I'm going to give you a random set of numbers. And again, these are completely random. There's no reason why I'm picking them. Just a random set of numbers. And let's say I had to find the mean of these numbers. How would I do that? Now, there's multiple ways to do this. You could do it the normal way, which is just using the formula. The formula for mean is the total of all the numbers divided by how many numbers you added up. So if I were to solve this by hand, I would literally add up all these numbers, and then we added up 7 different numbers, right? 1, 2, 3, 4, 5, 6, 7. Yeah, we added up 7 different numbers. So then you would just divide everything by 7. So it's the total of all the numbers divided by how many numbers you just added up. That's going to be the mean. Okay, it's actually a shortcut for this, which we'll talk about later about assigning. Actually, let's just go over this. Okay, so if you type in a list of numbers in Desmos and you put brackets around it, Desmos will recognize that as a list. And you can assign that list then to a letter, let's say, and we can just keep on using that letter and it's going to automatically use that list over and over again. Now, why is this helpful? Because you can't copy and paste on the SAT testing software. On Bluebook, the SAT testing software, you can't copy and paste. I can copy and paste here because I'm not using Bluebook right now. I'm just using Desmos.com, but you can't copy and paste on the actual SAT. So you have to work around it, right? You have to be shortcuts. So if you want to type in the same list over and over again, you can't. What you can do is just type in the list one time, put brackets around it, assign it to a letter, and just keep on using that letter over and over again. So why is this helpful? Let's say we want to find the total of this list. It automatically gives us the total. Let's say we're trying to find the mean of that list, that same list. It automatically gives us the mean. And yeah, you can type in mean. If you didn't know, shocker, right? You could type in mean and then type in the list of numbers. Obviously, I don't have to type this. I could actually just type in the list here too. Like 2, 1, 4, 6, 7, 9, 2. But it's going to give me the same answer. Okay, you can also type in median. Shocker, you can type in median too. There's also other you can type in min, but I don't know why you would need this. Obviously, min. If you didn't know, min is the smallest number, so you can just look and see what the smallest number is. You don't need to waste time typing it in. You can also type in max though. You can type in standard deviation, but you don't actually type in the word standard deviation. I guess 2 words. You type in the shorthand stdev and then type in A or the whatever you assign the list to. So you see, let's say there was a question that required us to find multiple different values for the same list. You don't have to type in the list over and over again. You could just type in A over and over again, or you can assign it to any letter, right? I can assign it to B as well, but then I would just need to use B here then instead of A. Let's go over median. Okay, how do you actually find median shorthand? Because it's helpful to understand the theory. How do you get this? Let's say we had this list of numbers and we had to find the median by hand. How do we do this? Now, first of all, you should order this numerically. I'm going to do least to greatest. I think that's the most normal way to do it. You could also do greatest to least, but as long as it's in numerical order, yeah, it's fine. So 1, 2, there's 2 2s. So 1, 2, 2, 4. I'm just going least to greatest, 7, 9. Okay, yeah. So I just took all these numbers, ordered them from least to greatest. Now the median is the middlemost number. And then just find the middlemost number. I think the easiest way to do this, and what most people do, is you just cross out the leftmost number, cross that out, cross out the rightmost number, and just keep on going. Leftmost number, rightmost number, leftmost number, rightmost number. And what you end up with is just the middlemost number, and that's the median. Okay, it's 4. Now, some people get confused. What if there's no middle number? What if there's an even? Right now there's odd. There's 7 numbers, so that's an odd number. So obviously it's going to be a middle number. What if I got rid of the middle number, and now there's only 6 numbers? So if I try that again, let's do that again. 1, 9, leftmost number, rightmost number. But what do you do now, right? If you cross these out, there's not a middle number anymore. So what you do instead is you take the 2 most middle numbers and you take the mean of the 2. What is, I guess you could think of it as the average. What is the average of 2 and 6? I think it's 4, but I don't trust my brain anymore, so the answer is 4. Okay, so the median of this is 4. Again, you still find the middle number, right? In this case, if there's 2 middle numbers, then you just take the average of the last 2. That's the median. Now, a super important skill that you need is the ability to be able to figure out what the mean is, at least a rough estimate of what the mean is, without actually doing anything. Just looking at the graph or the figure, you can tell immediately what the mean is. And I'll show you what I mean, okay? So let's say I have a random figure. I'm just gonna draw this, okay? What is the mean of this? That's it. Like, all you have is just this figure. Where would the mean be? I mean, you need set numbers, okay? Let's say this is 5, this is 6, this is 4. Sure. Okay, what is the mean? You should be able to tell. It's pretty obvious it's 5, right? It's pretty obvious. Now, the mean is the balance point, okay? And again, mean is the average set of numbers. It's the total amount of numbers divided by how many there is. That naturally gives you the average. But I only think of mean as the balance point. So if I have a figure, imagine this figure was 3D, right? I guess it's a hat. Imagine there's a hat. Where would you place your finger at the bottom? If you could only place your finger at one place at the bottom to balance the entire figure, where would you put it? You'd probably put it around right here. I think that would probably, that's your best guess for balancing this entire thing. That's the mean. So I want you to think of the mean as the balance point. So it's super important. It saves tons of time, okay? You don't have to type in all of these to figure out the mean. You just look at the figure immediately and know. Okay, this one's pretty easy. Let's do a slightly wonkier one. Let's do this one. I'll smooth that over. I've been out of room on my trackpad. Okay, there we go. Pretend that's a figure, right? And I'm gonna give you a bunch of numbers. 2, 3. It could be like 2.5 though. Okay, so it doesn't have to be an integer, obviously. Where would you put your finger to balance this? Like, what's the mean of this if you had to guess? My guess would probably be, I think, probably around here. Not exactly 4, but I would probably put my finger around here at the bottom here. If you could only put your finger one place at the bottom to balance the entire thing, maybe it is 4. It's around 4, I think. Like, I would think I would put my finger here, but you get the idea, okay? If you didn't know this before, I think this is a great skill to have. I was being to figure it out because the SAT, if there's a ton of data points in a question, it is not worth it to type everything out. You can just basically guess what the mean is, because if there's a ton of data points, I promise you don't need to get the exact mean. I promise you don't. You just need to have an idea of like, oh, maybe of which mean is higher, maybe. Like the question might ask you, this figure versus this figure, which one has the highest mean, right? And you should just be able to tell, because it's pretty obvious. Like this one is around 5. There's no way the mean of the here is 5 or greater, right? It has to be less than 5. So you know immediately this one has the greatest mean. So it's just the ability to be able to figure out like a rough estimate of what the mean is just by looking at the figure. That's super powerful. You need to know that. And there's also tons of other skills you need involving that. Okay, let's say the question asked us, what is higher, the mean or the median? And all they gave us was this. Okay, they just gave us this picture. And you have to figure out what is higher, the mean or the median. What would you think the answer is? Because you need to be able to figure out what the answer is without doing anything other than just looking at the graph. Okay, this is a super important skill you need, okay, because this will go a long way. It's going to save tons of time for you as well. You might have noticed that the mean and the median, they're pretty much both doing the same thing. They're measuring the center of a set of data. So basically the average. It's trying to give you the measure of the center of a set of data points. So why do 2 different ways to measure the center? Why do people just not use the mean every single time? But why do people still care about the median? And the reason why is because the mean, while it is technically a better measure of center, it gets influenced more by unusual features. For example, if I were to add an extremely high number, let's say 100, to the set of numbers, it completely messes up the mean. However, if I took the same exact data points and I typed it in median, it doesn't mess up the median that much. You see, the median changed from 4 to 5 by adding an extremely big number. However, if I add an extremely big number to the mean, it goes from 4 point something to 16 point something. But if I add an even bigger number, it goes to 128 point something. But add a bigger number, it doesn't even change the median at all. So you can see the mean is not resistant at all. It's very influenced by some random data points that don't match the other statistics, right? That don't match the other data sets. So you can see that the median is very resistant to unusual features, like just a random data point that is way out there that doesn't match any of the other numbers in that data set. It's very resistant to that. So if there's an outlier, it's not going to be influenced versus the mean, it is. And this goes with just looking at the graph as well. Okay, it's pretty important you understand this. So let's say I have this. If I were to draw this out, it probably looks something like this, and way out here, right? Because there's a random data point in the thousands. If I were to put my finger somewhere here, I'll probably put it like around here, right, to balance that weird shape. Probably put it around here, right, to balance it, right? But the median, it doesn't care about that. Like you just cross out the leftmost, rightmost, leftmost, rightmost, and this just becomes one of the numbers you cross out. It doesn't matter how big that number is. And that's why the median is resistant to unusual features or to outliers. And that's why we use the median instead of the mean sometimes. Let's say we're trying to measure a statistic like average annual income. You can see that the average annual income here, it uses the median. It doesn't use the mean. I switched up average annual income and it gave me the median instead of the mean. Why does it give me the median when I ask for the average? It's because there's a lot of billionaires. Okay, there's a lot of really, really rich people that skew the data. Okay, you can imagine if there's a billionaire, but most people earn around $40,000 every single year, but there's a billionaire that earns many, many, many times that. If you were to take the mean instead of the median, this number would be way higher than it should be. Okay, if you want want an accurate representation of the average person, in this case in the UK, because I'm using the VPN, so it's in the UK. But if the average person, if you were to pick like a random person from the street from the UK, you want a general estimate of what that person is earning. Obviously, if there's some billionaires out there and there's tons of rich people, like millionaires out there, you don't want those people to skew the data because you just want an accurate representation of the people living in the UK every day. Right? You don't want this random billionaire messing up the data for everyone else. So that's why the median is very helpful. It's very resistant to unusual features, like somebody owning way more than everyone else messing up the data. So having said all that, does that help you answer this question? Which one is higher, the mean or the median? Okay, I want you to think about this. Okay, so unusual features, right? Where's unusual? So there's basically really low data points here. There's not a lot of them, but there are some very, very low data points that don't really match the rest of the data points here. Okay, what is that going to do to the mean? It's going to pull the mean this way. But again, the mean is not resistant to unusual features, but median is. Median will generally give you the center of a set of data points, right? You just cross out. It doesn't matter that this is 2 and that this is 5. You're just going to cross it out. Okay? It doesn't matter how big the difference is between them. But for the mean, it does. If there's a really, really small number that's very different from most of the numbers, it's going to pull the mean that direction. So for the answer to this question, which one is bigger, the mean or the median? It's going to be the median, because the mean is going to get pulled this way by the abnormal small numbers on this side. Hopefully that makes sense. The median is probably going to be really smack dab in the middle of this big clump here, right? Because most of the data points are around here. So it's going to conquer around here. Hopefully that makes sense. Let's do another one real quickly. Okay, so if I have this shape, which one's bigger, the median or the mean? You should say the mean, right? Because this time, the more unusual features are on the right side, right? The bigger numbers, right? So the mean's going to be bigger because these unusual features, these bigger numbers are going to pull the mean to the right more, right? To the bigger number side. But the median is probably going to be around here, right? It's like smack dab in the middle of this big clump. But the mean is going to get changed. It's going to probably be like around here now instead of there because of all these numbers here. Okay, so hopefully that makes sense. If you can answer this question, believe it or not, you've mastered mean and median. This is probably the hardest mean median question that the SAT asks you. So if you understood this, why the mean is greater than the median here, then you're set. You're going to be able to solve every single question that has something to do with the mean or median on the SAT. Now, let's just keep on going down this list that I made. So the mean, median, we went over that. Minimum and maximum. You should know what minimum and maximum means. In case you don't, the minimum is the smallest number. So if I have this list, the minimum is going to be 1. Right? And again, I told you, you could just type in min b2. I don't know why you would need to do this, because you just look at the data points and just see which one's the smallest number. I feel like it's a waste of time to type in min. I would just make sure you understand minimum is the smallest number. The maximum is the biggest number. The maximum is 9 here. Now the range, right? The next statistics that you need to know, the range is the difference between the maximum and the minimum. So what is the smallest number? What is the biggest number? And you just subtract the two, right? What is the positive difference between the two? So you take the biggest number. So in this case, the biggest number is 9, right? 9 was the smallest number, 1. So 9 minus 1, the range is 8 for this data point. Okay, it's the difference between the biggest number and the smallest number, the difference between the maximum and the minimum. Now let's go over standard deviation. I think standard deviation is probably the hardest, although it's not even that hard if you just watch this video and understand what I'm saying. Standard deviation is actually pretty easy, but it trips a lot of people up. So make sure you pay attention to make sure you actually understand this. Now, you don't actually need to be able to calculate standard deviation. I've never in my history of the SAT actually used stdev on the SAT. I've never used this. Okay. You never actually need to find the actual standard deviation of a question, because standard deviation questions on the SAT, the most they'll amount to is just comparing two data sets and asking you which one has highest standard deviation, which one has lowest standard deviation, or if these standard deviations are equal. Right, so I'll give you an example. Let's say I have 3 different graphs. Okay. I have this graph. I have this graph, and I have this graph. Okay, sure. I try my best. I'm trying to draw on my trackpad. I'm sorry if it looks really bad. Okay, but you get the general gist. Okay, you have 3 shapes. Okay, this is shape 1, this is shape 2, this is shape 3. And you had to find the greatest standard deviation. Okay, it would be helpful if I told you what standard deviation means if you had no idea. So let's go over that. Standard deviation is the measure of spread. Okay, how spread out something is. So the more spread out something is, the higher the standard deviation. I think that's the easiest way, and it works every single time on the SAT. So just remember it like that. Okay, how spread out something is. Now I'll give you more examples and more definition standard deviation in case that one didn't click. But for now, which one looks the most spread out? 1, 2, or 3? You should have said 3, hopefully. This one's way more spread out than 1 or 2. You can also think of standard deviation as the smaller the standard deviation, the more clumped the graph is. Okay, so this one is very clumped, right? It's just dead set in the center. It's just clumping together at this middle point. Okay, so this one has the smallest standard deviation because it's clumping the most. Or you can think of it as it's spread out the least. Okay, so that's why it has the least standard deviation. Again, I told you 2 different definitions, I guess. Which is it's basically the same thing, okay? The more spread out it is, the higher the standard deviation, or the more clumped it is, the smaller the standard deviation. You think of it as either way. And this one is in the middle between 1 and 3, right? This one, it is clumping, but not clumping as much. Like you see, this one's clumping a lot more. Like this is, out of all data points, more of them tend to land in this clump than this one, right? This one is clumping less than this one. So this one's in the middle, okay? It's not the least standard deviation, it's not the most standard deviation, it's in the middle. This one is, there's not even one clump, right? It's clumping 2 places. It's not as clumped as these for sure. This one's clumping the least. So that's the most. So it's most spread out because it's clumping the least. I think the official definition of standard deviation might help you a lot if that confused you. It's the one I use to figure out something has greater or less standard deviation. Standard deviation is the measure of variability, how much something varies from the mean. So for this graph, the graph number 1, what would be the mean? As we said before, we could just relatively guess. The mean's obviously dead smack in the middle, right? This is the mean. Now, the data points, they tend to not vary much, okay? Like they tend to vary a bit, right? You can see there's some variation in terms of where they fall next to the mean, but it's pretty close to the mean, okay? So this has a small standard deviation. It's how much something varies. You see, this doesn't vary much. Compared to number 3, what is the mean? If I were to balance this weird looking shape that's poorly drawn, I'd probably put my finger around here-ish. Yeah, like I would say that's about the mean. It's just eyeballing it to balance this figure. What is the variability here? Okay, like most data points don't land here. Most of them land around here, right, and here. So you see, this one varies a lot more than this one. So because this one varies a lot more, it has a higher standard deviation. Okay, standard deviation is how much something varies from the mean. Same thing here, right? The mean is around here. It does vary, but it varies slightly more than this one, obviously, right? But it doesn't vary nearly as much as this one. So this one's in the middle, right? It varies about in between 1 and 3. So that's how you can think of it as well. Whatever way it works. I personally prefer to think of it as how much something varies from the mean, but you can also think of it as how spread out something is, or how little it clumps. Okay, so if it clumps a lot, then it has smaller standard deviation. Either way it works. Either way you want to think about it. But as long as you can do this, as long as you figure it out, right? As long as you understand why number 3 has the greatest standard deviation and why 1 has the least standard deviation, then you're set. Okay, that's all you need to know. I promise you, like that's the hardest standard deviation questions we'll get on the SAT. It's not that hard. As long as you understand that, you're fine. Now, there was one other statistic that I didn't mention here because I've never seen the SAT test it, but I'm just gonna go over it real quick just in case they do test it. I wouldn't be surprised if they tested it, but I've never seen it tested on the SATs. It's mode. Okay, what is mode? Mode is also a measure of center. Again, mean and median were measures of center. It's around the average of what you're looking at, right? Mode is kind of the same thing. Mode is just the most common number. That's it. So if I look at this data point, what is the most common number? It's 2, right? All the other numbers only appear once. 2 appears 2 times. So the mode here is 2. So mode is just the most common number. It's really easy to know. Okay, if I were to get rid of 2 here, what is the mode now? I pretty much, I think you can go either way. Either there's no mode at all because none of them appear more than once. Every single number appears the same amount of times. Or you can think of this as all of these are the mode, right? You could say you'd be correct if mode was 4. You'd be correct if you said the mode was 1 and all the modes. So yeah, that's mode. Okay, it's the most common number. If there's multiple numbers that appear the same amount of time, then it's just both of them, right? So if I say 2 and 1, the mode here is 2 and 1. But you don't take the average of 2 and 1. It's just the mode is 2 and 1. That's what you would say. Hopefully that makes sense. Rewatch that. I just kind of breezed over that because I don't even think they're going to test it. Because I've never seen the mode being tested. If that confused you a lot, just rewatch the last portion about mode just to make sure you understand it. Now that is pretty much it for these metrics, you could say. But I want you to understand one last thing, and that's the difference between the measure of center and measure of spread. Okay, as we said before, the measure of centers, right? Mean, median, and if you see mode, then mode 2. That's a measure of center, right? It's kind of like a measure of average. Like what is the center of a set of data points? There's also a measure of spread, and that's range and standard. I guess you could think of it as min and max too, because you can see like how much something varies. But the measure of spread is how much something varies, right? How spread out something is, right? There's multiple ways to measure that, but it is range and standard deviation on the SAT. That's it. Okay, standard deviation and range, a measure of spread versus a measure of center. Now, what's the difference between a measure of center and a measure of spread, other than just one of them is the center with the average, and one of them is how spread out something is? This has to do with transferring data points being changed. So if I have just this data set right on the screen right now, and I were to add 5 to every single data point on here. So every single data number I have that falls onto this graph, I just add every single data point by 5. So what would happen if I just added 5 to every single data point? Okay, we can go to Desmos just to better demonstrate this, okay? So if we have the mean, right? Look at the mean. And we added 5 to every single data point in here. What would happen, right? You notice the mean is just going to shift up 5 if I add up 5 to all of these. There's a lot of data points here. You can see the answer was 4.42. I mean, the mean was 4.42 before. Now it's 9.42. So you just added 5. So if I add 5 to every single number here, it's just going to shift the center up 5, right? You can look at this graphically too. So if I were to just extend, if I were to extend this, right, and let's say there's so 7 would be here, so up 5. But basically, I would just not change anything, but just shift this thing up by 5. Like this would just move up 5. If I added 5 to every single data point here, it's just going to move every single data point here up 5. So it's just going to shift the graph up 5. So the center, measure the center, so the mean and median, I guess mode too, right? They will all move up by 5. So if you add 5 to every single data point, it's going to add 5 to every single data point here. Now, what happens if I multiply by 5 instead of adding? So if I go back to this, right? If I multiply by 5, it's actually going to be the same thing, right? You just multiply the mean by 5. I'm going somewhere with this, okay? I just want to understand what I'm talking about so far. So if I multiply 5, right? The mean was 4 point something. So if I multiply, or like around 4.5, right? If I multiply this by 5, you see, yeah, that's basically what happens. So if I multiply every single data point by 5 instead of adding them, because before it was adding them, but now I'm multiplying. You just multiply every single data point by 5, it's gonna just shift everything up by, I guess, multiply by 5, right? So I'll just kind of graph what it's going to look like. So if I have the original data points, I have this original thing, and I extend this line, what's going to happen? What's going to be the transformation that happens when I multiply everything by 5? So if I take 1, let me just get this. So 1 times 5 would be 5, right? So 3, 4, I'm just going to draw like a 5 here, okay? So you see like around the start of this figure is going to be at right here, right? Because all the starting figures get multiplied by 5. 2 times 5 is going to be 10, right? So let's get a 10 going here. You can see it's gonna, this figure is gonna go like around here, like the top of it, the mean or the median also is going to be around 10. And 3 times 5 is going to be 15, right? So let's get 15 going here. You can see what happens to this. It's a pretty drastic change, right? So not only did the graph shift up by 5, right? It did, or not by 5, right? It shifted by a multiple of 5, right? So the mean went from 2 to 10. So this shift up. But also what happened was the entire graph got bigger. It got more spread out. And you notice before this one, it didn't really do anything to the shape of the graph. All it did was just move the graph up. But if you multiply, it's going to change the spread. So that's the difference between, at least one of the differences between center and spread. So measures like mean, median, mode, they do change, okay? They change when you add them, when you add numbers and when you multiply numbers, okay? However, measures of spread don't change when you add numbers. Notice when I added 5 to this graph, it did not change the shape. Like the spread is still the same. But if I took the standard deviation of this, like the mean would be here, and here's how much it varies. It's still going to vary the exact same amount as it did here, right? The variation doesn't change. Like the measure of spread doesn't change. Same thing with range, right? The highest number minus the lowest number, the highest number minus the lowest number, that doesn't change at all. The measure of spreads don't change because the shape is still the same. It is the exact same shape. The measure of spread is really the measure of shape, like how spread out something is, like the shape of the graph, right? So the shape didn't change. Obviously, the min and max does change. It does change, right? Because the max and min grow bigger. So you could think of it as that. But really, the most measures of spread, range and standard deviation, the ones that have to do with how much something varies, how like the shape of something, those don't change at all when you do addition. And this only goes for when you add every single number by the same amount, like every single number in here by the same amount. So you basically shift the entire graph up. Okay, if I only added 5 to one number here, obviously that's going to change. The shape's going to change. I'm just talking about when you add the same number or when you subtract the same number to every single data point, then only the measure of the center will change because the center is going to move, right? But the shape doesn't change at all. But when I multiply or when I divide, it's going to change. You see like how much it changed. Well, this is my best guess of like the graph of this. I don't think it's going to get bigger, honestly. I think it's going to look like something like this, actually. It's not going to get that big. But you get the idea, right? It gets way more spread out. The range is definitely going to change. It went from 3 minus 1, which is 2, right? The range was 2. Now it's 10. Okay, you notice the range increased by a multiple of 5 too. And standard deviation, it changed too. Right? It's a lot more spread out now. You don't actually need to know. I personally don't think you need to know like how much something actually changes. Like you don't need to know that if I multiply every single data point here by 5, it's going to change the range by 5. I don't think you need to know that. I've never seen SAT actually test that. But you just need to understand that the range and standard deviation or the measures of spread is going to change, but it's not going to change when you add or subtract. Okay, because they're just a measure of the shape, and the shape doesn't change when you add or subtract. So far, I've gone over everything that has to do with measures of center and spread. Now let's talk about the different figures, the different different ways data can be presented on the SAT. And it's pretty important you know all of these, or all 5 of these, because the SAT does test all 5 of these. I don't think they test anything more than these 5 though. So it should be pretty simple, hopefully. Most of these are really easy and you already know them probably. The first figure we're going to go over is a dot plot. Now, what is a dot plot? Let's just list some things you might keep track of. Okay, let's say colors. Okay, we might keep track of how many colors, how many different types of colored marbles maybe that are in a bag. Okay, there's red. I'm gonna do B for blue and Y for yellow. I'm not gonna actually, I'm too lazy to write it out. That's a B, by the way. When I'm tracking marbles, let's say I'm pulling up marbles from a bag, right? And I pull out one marble and it's a red marble. I'm gonna put one dot in front of red. On top of red. I pull up another marble and it's yellow. Okay, I put one dot on yellow. And I pull up another marble and it's red. So I put another dot on red. Pull up another marble, it's blue. Put a dot. So you get the idea. This is a dot plot. Okay, how many dots on top of a thing you're tracking? That's how many things there were. Okay, so there's 3 blue marbles. And if blue is how many blue marbles there were, and there's 3 dots on top of blue, then that means there's 3 blue marbles. Okay, if I put another dot, it's 4 blue marbles. Same thing here. And if I put 2 dots, then there's 2 yellows. If I put 3 dots, and there's 3 yellow marbles. Okay, hopefully that makes sense. It's very self-explanatory. This is pretty much the same thing as a bar graph too. A bar graph, instead of dots, there's going to be a y-axis now. The y-axis is going to tell you how many there actually were. So let's say on here we say 5. It's going to go by 5 increments. 10. Okay, it's going to be a y-axis. And the bottom here, let's go red, blue. Yeah, red, blue, yellow again. Okay, but this is a bars there's bars instead of dots now. Okay, and the bars are gonna go up to like a number, right? So here's a bar 5. This is gonna go up to, let's say, 10. Okay, and this is like in between, like I would say 7.5. So this is the same thing as a dot plot, but now you have to look at the y-axis. Like, where does the bar end up on the y-axis? Oh, so it ends up at 5. So there's 5 red marbles here. Oh, there's 10 blue marbles here. Oh, there's 7.5 around. Yeah, 7.5 yellow marbles. Okay, so that's the difference between dot plot and bar graph. Do the same thing, but one of them's a bar and one of them's a dot. I'm actually going to skip histograms because histograms are pretty complicated. They look the exact same thing as a bar graph, almost the same. I'll go over that in a bit. I'm going to talk about frequency tables real quick because frequency tables are the exact same thing as the dot plot pretty much. Okay, so a frequency table, actually, I have an example. Let me go down to it. This is a frequency table. Okay, a frequency table, pretty much the exact same thing as a dot plot, but instead of dots, it just tells you how many there are instead of dots. Okay, so this is the values, right? Let's think of this as like the colors of the marbles, right? And then the frequency is how much of each, or how many dots were on top of that marble. So in this case, there's one book with 46 pages, or you can think of it as 1 red marble. Okay, there's 2 blue marbles. There's 4 yellow marbles. There's 5 green marbles. So you get the idea. So this is the frequency. This is the same thing. So it's just like pretty much a dot plot on its side, and you, instead of all the dots, you just have a number of how many dots there were. That's a frequency table. Now, a ton of people get frequency table questions wrong because of a very, very stupid, silly mistake that pretty much everyone makes at one point. Okay, and you might even understand how frequency tables work. Like, this is the frequency, and this is the values, right? And the frequency is how much of each value appears. You might understand that, but even then, you're still going to make the silly mistake. Is most of you will. And I want you to be the one person that never makes the silly mistake. Okay, make sure you understand this. A lot of people confuse frequency for the value, even if they understand. Even if it will say frequency, but it will literally say frequency at the top there. But you're still going to think of this as the value because you're just not going to think. And when you make the mistake, you won't make it again. But hopefully, you don't make this mistake in the first place. Ideally, don't make this mistake during the actual test. That would suck. The mistake is they confuse frequency for the value. So they pretty much just ignore this column for some reason, and you just look at the frequency and you're like, oh, 1, 2. So these are the actual values of appears. Right? So there's 1, 1. There's 2 2s that appear. There's 4. There's 2 4s. There's 3 5s. They think of it like that, and obviously that's gonna, like, let's say the question asks you they give you 2 frequency tables and they ask you which one has the least standard deviation, and then the other one has frequency tables of just like frequencies of 5s just down the line. And that person's gonna be like, oh, it's only 5s. It doesn't vary at all because it's just 5s, right? So the standard deviation is gonna be really low. So let me pick that one. That one's the lowest standard deviation. No, okay, that's the frequency. Okay, I would encourage you to actually graph it. Graph the frequencies. If you see a frequency table, actually graph it. Don't just like look at it. Just to avoid this common mistake. Okay, so what I mean is, let's say there's one frequency table with just 5s. Okay, there's these values, the same exact values, but all you see down the line is 5s in the frequencies. What is that going to look like if you actually graph it? Like, what is the thing going to look like, right? If we have this line and we have, like, let's say the values are down here. Okay, they're only 5. So it's just going to look like this. It's going to look like a flat line. Now, that has a huge standard deviation. It's just as spread out as you can get, right? I'm not sure if it's as spread out, but it's very spread out, okay? Versus, let's say this graph. If I were to graph this, this, and here's the values. What is this graph going to look like? I think it starts out pretty low, right? It starts out only one value, and then it goes to 5 pretty rapid. So it goes to like here, there's a hump here, and then it goes down here, and then it goes back up. So it looks kind of like this. Okay, I just tried to do so basically I'm just imagining like how many dots are in front of each value, right? So at 46 is only 1, at 47 there's 2, so you increase it goes higher up, and there's 4 here, and then there's 5 there, and then yeah, so it's obviously not accurate, not that accurate, but it's a rough sketch of what this will look like if you were to turn this into a dot plot, right? Versus this. Which one is more spread out? I would say this one actually has the higher standard deviation than this one. So this one actually probably has less standard. It's more clumping at least. Like it's clumping more. Right? So this one actually has least standard deviation. So you would get the question wrong if you thought of these as the frequencies as the values. Okay, so don't confuse it. I just want to clarify that. You might think it's a very stupid mistake. You're not going to make it, but I would say probably 70% of you are still going to make this mistake. It's just what it is, because I don't know, like just doing a lapse in judgment maybe, and your brain just doesn't work. Okay, but once you make the mistake once, you're not going to make it again. I just want to explain it either way because I tried. Okay, so now let's go over histograms. Okay, we have histograms and box plots left, but let's go over histograms. Box plots are super easy. Okay, histograms. You need to know the difference between a histogram and a bar graph because they're very different. Okay, they look the same though. They pretty much look the same. So here's a histogram. Okay, let me draw this out. See, I'm gonna make it look the exact same too, just to confuse you. So this is a histogram. So what is the difference between a bar graph and a histogram? Now, histograms, the x-axes are ranges. So this is actually saying between 0 and 5, and between 5 and 10, and between 10 and 15. It's probably clicking what the difference is, but let's give you an example. Okay, let's say, I don't know, we're trying to track grades. Okay, like a grades on a test, and the max grade that somebody could get was how many questions there were. There were 15 questions on that test. And then we're trying to track how many questions did each student get correct. At least like what range they fall into. So let's say the first student's test we looked at, they got 3 questions correct. Okay, so 3 is in between 0 and 5. So this would get 1 tick mark, I guess. Like, yeah, that student would contribute to this bar one time. Okay, and then we pick another student, we look at their test, and they got a 12. They got 12 questions correct. Then they would increase this bar by 1. Now we look at another student and they got 7 questions. And we look at another student and they got 9 questions correct. Then we would tick 1 here. So you see a histogram is slightly different than a bar graph. A bar graph really just counts just one day or how much of this thing happens. So histogram, it's more numerical data, right? And it tracks how much of each thing falls under a certain range of numbers. That's a histogram. Now, why is this significant? Like, why do you need to know the difference between a histogram and a bar graph? There are questions that specifically test you on this knowledge, okay? The idea is you don't even know on a histogram, you don't even know what the numbers in here are, right? If somebody just showed you this histogram and just told you, okay, this was people's grades on the test, right? How many questions people got right on the test. You don't know if every single student in like 5 students only got 1 question right, or 5 students got 4 questions right. Because all you know is that it falls under this range of between 0 and 5, but you don't know what the actual number is. Like, it could be that 5 students got 4 questions correct. It could be that 2 students got 1 question correct, 3 students got 3 questions correct, right? Or like, so whatever combination, right? You don't know. So that's the idea. So let's say an SAT question asked you, what is the greatest possible mean of these grades? If we were to take all these students and take how many questions they got right, and we got the mean, what is the greatest possible mean? Because we don't know exactly what the mean is, right? Because we don't know exactly what the numbers are. We just know they fall into this range. So how would you get the greatest possible mean? You just have to have the highest numbers, right? So you just take all the highest possible numbers from each bar. So let's say all 5. Oh yeah, this is also another thing that you need to pay attention to. The question will tell you this, by the way. There won't ever be any debate over what this is. But you notice if somebody gets a 5, if they get 5 questions correct, do they fall into this bar or do they fall into this bar? You don't know, right? The question will tell you. It'll tell you. Like, it will say, oh, like this range is between 0 and 4. They take 1 bar here, and then this range between 5 and 9. Okay, so let's say that. Okay, so this is, if they got a 5, it gets into this bar. If they got a 10, it gets into this bar. So it always, yeah. So the maximum for this one is 4. So how would you get the greatest possible mean of this histogram? You would assume that everyone got 4s, and everyone got 9s here, and everyone got 14s. So 14, so you would add up 7 point, I guess let's say 8. Okay, 8 students got 14s. And then you add that, you get the total. So you would get 8 14s, 10 9s, and 5 4s. Okay, and then you would get the mean of all that. Right, so you add all those up, and then you divide it by how many students there were. And then that would be the greatest mean. And if you get the smallest mean, then you would go for the smallest numbers. Right, so 10, right? 10 because 10 falls into this one. So we had 8 10s, we had 10 5s, we had 5 zeros, and you get the mean of those. That's the least possible mean. Okay, so again, it's the idea that you don't know exactly what the students got. Okay, as long as we just know that 5 students got something in between 0 and 5, but we don't know exactly what they got. So the SAT might test you on that, and they might try to quiz you on that fact, and you have to understand that, so be able to tell, oh, if I were to get the greatest possible mean, then I would try to, then these students probably got the greatest possible numbers, and you try to get the answer that way. And last but not least, let's talk about box plots. Box plots are super easy, okay? It's really easy. The SAT, I've never even seen it test you on interquartile ranges, or this quartile or this quartile. It doesn't never test you on that. So you don't even have to know what the heck these things have to do with anything, okay? All you need to know on a box plot is that the middlemost line is the median. Okay, not the mean, it's the median. I've had students get confused and thought it was the mean. It's the median, okay? The one where like you have to organize from least to greatest and get the center. That statistic is the median. So the middlemost number, the line inside the box, middlemost line, that's the median. And the leftmost and the rightmost, that's the min and the max. Okay, so this is the minimum, this is the maximum, and this is the median. That's all you need to know for the SAT. So if you see a box plot, or it might be called the box and whiskers plot, but I think on the SAT they only call it box plot, right? It says box plot. Right, so if you see a box plot, that's all you need to know. How to get the median, how to get the min and the max. Okay, so pause the video and try solving this question. It should be fairly easy, but try solving it real quick. Okay, hopefully you looked at it. So it says daily high temperatures in degrees for a city, okay, are summarized in the box plot. Which of the following is closest to the median of the high temperatures in degrees Fahrenheit of the city? Okay, so what is the median temperature basically? So the median again was the middlemost number. That's around between 41 and 42.5, I think. Wait, no, I don't know. So 41, that's 43, right? So it's like 42-ish. Yeah, and then you just pick 42. And you see, because the SAT won't ever give you like, it's iffy like what the answer is, right? And that's never going to make you do that. Right? It's not going to be 42 and 42.5 as the answer choices. It's going to be pretty hard. So yeah, even if you didn't exactly like figure out 40, it's pretty obvious, right? 48, that's way over here. 35 is way over here. So the only one that's remotely close is B, 42. So you just pick that one. Okay. And see, it's really easy. Box plots are always super easy questions. You just have to know how to read it. This is the medium, this is the min, this is the max. That's it. Now let's do this question. I did show you the frequency table for this question before, but we didn't actually solve it. So pause the video and try solving this. And then we're going to go over it. Okay, so this question says Paulina has 28 books in her collection. The frequency table summarizes the number of pages in each book. If she buys a new book that has 62 pages, how would this impact the mean and median number of pages of the books in her collection? So hopefully you remember what I said about the mean being not resistant to unusual features or outliers, and the median is very resistant to unusual features. So if I add 62, like right now the range is between 46 and 53. If I add a book that has 62 pages, it's going to be like way over here. It's a higher number of pages than everything else. It's going to pull the mean this way. The mean's going to be very influenced by this huge number that's not like the other numbers, right? The median is not going to be influenced by a lot. Now, honestly, I would like actually go and find the median myself just to be 100% sure, but I've never seen it the case where the median actually changes for like any unusual, like when they add a new data point to a set, like those types of questions. I've never seen the median change, but we can see. Let's just do it real quick, okay? Because this is what I would actually do during the SAT. If you stop for time though, just assume the median doesn't change because it's very unusual, resistant to unusual features. It's probably going to be right. The mean will increase, the median will stay. It's probably C. That's what I'm guessing. Okay, but let's do it quickly. So it's already organized from least to greatest, kind of. Yeah. So I have to keep track of. So we have to get the median before the change and the median after the change. Let's get the median before the change. We'll cross out like the leftmost and the rightmost, right? So there's one tick mark here. 2, so there's 2 tick marks here because there's 4 in here, right? 1. Okay, so this one's complete gone now, and there's 3 left in this one. Okay. And so 5, there's 3, and then there's 2 gone here. So there's 3 left. Hopefully this makes sense what I'm doing. 2 here, so there's only 1 left here now. And then, so there's 1 left here. Okay, so the median is definitely in the 5s, right? We cross out 1, and then there's 4 left in here. So then there's just 4 50s in this. Yeah, I'm not going to write out 4 50s, but you get that. There's going to be 4 50s. And then if we find the median, it doesn't matter. It's just going to be 50. Okay, and so right here in the middle of this. If we were to increase this by another one, because there's going to be a 62 way over here, so there's going to be 1 less tick mark now on the right side here. It's just going to move it 1 time, so it's going to go from 50 to 50. So you see the median doesn't change at all. Okay, the middle number does not change. It's still going to be 50. Then we know the median doesn't change. The mean does change, obviously, because there's a bigger number now. It's going to pull the mean this way. So the answer is C, right? And as I said before, I've never seen the case where the median actually changes. I've never seen it. When you add a new point, it's going to ask you like the difference between mean and median, what changes and what doesn't. The median has never changed ever. ever. This is the pattern I've noticed. Okay, let's do one last question. Okay, this is going to be the last question we're going to do for one variable data questions. Okay, and this will just be a nice lesson for you. So try solving this question. Pause the video and try solving it. I'm going to zoom out a bit more. Oh, shoot. So you can see everything. Okay, hopefully you tried solving it at one point. Now let's read it. Why is it not zooming in? Oh well. Okay, I'll just read it. The 22 students in a health class conducted an experiment in which they each recorded their pulse rates. Okay, so it's heartbeats, right? And yeah, okay, before and after completing a light exercise. Okay, so this is before and after. Let S and R be the standard deviation range respectively for days before. So S1, okay, so this is standard deviation range, S1 and R1 for the one before it, and let S2, yeah, so the 2s are the one after it, which the following is true. So we just need to compare the standard deviation and range before and after each one, right? So let's look at standard deviation. So standard deviation between the one before and the one after the exercise. You see the shape, right? Standard deviation is how much something varies. If we look at the shape, this is definitely way more spread out than this one. This one's clumping together in the middle. So standard deviation for this one is way bigger. You can also think of it as what's the mean and how much does it vary from the mean. So the mean right here, obviously, right? It's really, if you were to balance this, it would be right here, and it's varying. It's not varying much. This one's varying a ton, right? It's varying a ton. So this one varies way more. This one has way higher standard deviation. So let's see if we can get the answer just from that, actually. So if we look at the answer choices, we know S2 is greater than S1. Standard deviation for this one is greater, right? So A is definitely wrong because we know S2 is greater. B is correct. Yeah, that's good. C is wrong. D is also correct. I bet a lot of you picked B. Okay, a lot of you just didn't even look at D or didn't fully understand what D was saying, and they just picked B because they just, oh, I got a right answer. Like B is correct, and then you just really skimmed the rest of the answers. You didn't really understand them. It's really important that you are super careful. Okay, verify answers. Whatever you can to verify answer choices, do it. So in this case, you can obviously verify an answer choice by checking all the other answers and see if they're correct or not. Or you can check the ranges too. Okay, like it says standard deviation and range has to be both correct. Like the R2 has to be greater than R1. So see if that's correct before you actually select B and go with it. So just be more careful. Okay, make sure you take advantage of all the different ways you can verify the answer if there is some. Ranges. Okay, what's the range? So again, range is the difference between the maximum and the minimum. The highest or the smallest. Right, so the highest for this is 88, the smallest is 56, 32, right? 88 minus 56 is 32. Yeah, you could type in the calculator if you want to. Knowing me, during the test, I would actually pull up the calculator and type it in. But I'm pretty confident. Okay, that's 32. Okay. 1112 minus 80 is the maximum minimum. That's also 32. You see, the range doesn't change. The range is the same between these two. They're both 32. The highest and the difference between the highest and the lowest is 32. So the ranges are equal. So the answer is D. Okay. B is wrong because it says the range for the second one is greater. It's not greater. Okay. If anything, they're equal, and D is correct then, because it says standard deviations are different, which is correct, and the ranges are the same, so that's correct. So the answer is D for this one. Okay, hopefully that was a good lesson on just making sure you're more careful when you're reading, and verifying your answer as well by checking the other answer choices if it's applicable. But that was one variable data. Hopefully everything I said makes sense to you. This is kind of important. It's a decent chunk of the SAT, so it's pretty important that you understand this, and more importantly, you understand how to get everything just by looking at the graphs. Okay, you should just be able to tell right away, just like looking at the shapes of two different graphs, which one has higher standard deviation like this. I can just tell immediately this one has higher standard deviation. You don't actually have to type in every single data point into Desmos and figure it out that way. You don't have to do that, and you shouldn't be doing that. Okay, you should just be able to tell. You should also be able to tell, if I add like a really big number, the mean's going to change. The mean probably isn't going to change. You should just be able to tell that right away. You don't actually have to like go into it and actually solve it. It's really important you have that skill, and you'll be able to tell roughly like what the mean is by looking at the graph. It's just important you do that. It saves tons of time as well. Hey, real quick, if you scroll down to the description and you click on the first link there, you'll be taken to my SAT course. There's a video I put together explaining what's in here. You'll get everything from 18 practice tests to one-on-one time with me. Okay, there's a lot. You pretty much won't ever need any other resource ever again for the SAT as soon as you get this course. There's also a really try-hard community in a good way. That's it. I just want to let you know it's here. Feel free to check it out. Now let's go over two variable data questions. And two variable data questions tend to be a lot easier. If you look at the distribution of this module, which is a lot easier than this module. Like if you look at the distributions, you'll see that two variable data questions appear a lot more on the easier module than it does in the harder module. And that's because when they're trying to choose questions for the easier module that require easier questions, there's more two variable data questions to choose from because two variable data questions tend to be easier. Okay, so two variable data questions are a lot easier. They're more self-explanatory. Okay, so I'll just go over the things that you need to know to solve two variable data questions. So this might be a shorter section because they're easier. Now, what is the difference between two variable data questions and one variable data questions? Okay, you might have guessed that the difference is that two variable data questions have to do two variables. What I mean by this is if we look at a two-variable data question, it's on the graph, right? There's an x-axis and a y-axis. There's two variables for this data point. When we were doing one variable data questions, every single data point only had one statistic, right? Maybe it was the fact that the marble was red or something, but there was only one statistic for that variable that we were keeping track of, okay? And then we might have kept track of how many of the red there were, but it was just one statistic. While there's two. Right, there's two different variables we're looking at. Okay, all two variable data questions look like this. Right, there's two different variables for a data point. Okay, you might not even realize that a question is a two variable data question just because it's really easy and you just solve it. But generally, any question that has something to do with two variables, right, an x and a y axis for like real life data, right, that's a two variable data question. Now, I think the most common type of question for two variable data questions looks something like this, where there's a bunch of dots and there's an estimated line for. It's called a line of best fit. Okay, you need to know the difference between the line and the actual points, or the data points, okay? And I kind of gave it away, but the data points, the difference is that data points are actual points, right? This is for charities, right? It shows data for 10 charities. So there's probably 10 dots here, okay? And each of these dots are actual points. They probably looked at the accounting books of these charities and looked at how much income they spent and what percentage of, I'm assuming, income they spent on total expenses, right? So they looked at, these are actual data points, and they graphed the 10 points for the 10 different charities. Okay, and afterwards they tried to estimate a relative line, like the direction. You can kind of see it's kind of going in a linear direction in this direction. They basically tried to make a line that best fits all these data points. Okay, and this is more for prediction purposes, because let's say we know one charity, we know that they earn 4,000 millions of dollars. I think that's $4 billion. That's a lot, but that's how much income they're earning. But we don't know what percentage of total expenses they have. We just know the millions of dollars of income, which is 4,000. We can guess based on this line, because this line is just a general trend. It's a model of based on actual data. It's just an estimate. It's like the average of all these data points, pretty much. Okay, it's just it's called a line of best fit. And if you know Desmos, which you should have watched my Desmos stuff. It's actually regression. It's the linear regression. So if I type in random data points, and I press this button, that's the line of best fit. That's how they calculate it, actually. So it's the same thing. It's kind of irrelevant, but just to help you connect dots, maybe things are lining up, like you're getting aha moments of like what the heck this meant. But yeah, that's that. Okay, so it's the line of best fit. It's a linear regression of all these things, and it's just a way to average it. It's a way to model the general trend of what's going on. So you can use this line now to predict more stuff. So let's say we knew a charity had 4,000 millions of dollars, but we didn't know what percentage of total expenses there were. So we could just find out, right? If we trace a line of 4,000, then we look at approximately, based on this model, this line of best fit, how much that percentage of income is probably around 86, 87. So we have an idea just from that. Okay, we can literally just use this line to make predictions. It's not going to be accurate. It's a prediction, but it's probably going to be relatively close, right? And that's the idea behind this line. Okay, so that's the difference. Okay, so if it says what's the actual percent, then look at the points, because those are the actual values. If it asks you something about prediction or estimation or something to do with those lines that's not actual stuff, then you look at the line. Okay, and that's it. That's majority of two-variable data questions, believe it or not. So pause the video, try solving this question, and see if you can do it. Then I'll explain it. Okay, hopefully you have time to solve it. So let's read it. The scatter plot above shows data for 10 charities along with the line of best fit. Yeah, as we discussed. For the charity with the greatest percentage total expenses spent in program. So it's talking about the y-axis, right? The greatest percent total income. So for the charity that has the greatest percent. So this one, right? This charity has the greatest percentage of total expenses spent on programs. Which of the following is closest to the difference of the actual percent and the predicted by the line of best fit? Okay, so we have to look at this and then the predicted in the actual percent, right? So it's talking about the x-axis, the y-axis. Okay, so if we look at this data point and we look at what was predicted for that data point, what is the difference? And then we look at which answer is the closest. So this one's at 92% probably, which is really high. And then this is probably around 85, 86. 92 minus 86 is 6%. And yeah, this is probably B. Yeah. So the other ones aren't even close. Like 4%, that would look something like this. Like the line would be like here, right? And then 10, the other ones aren't even close. So it's B for sure. Because hopefully that makes sense. I think the hard part is realizing, okay, actual and predicted. What to look for. Predicted is the line, the point is the actual. Let's go down here. So this is another common-ish type of two-variable data questions. Now, I want you to just jump straight into it. Hopefully you pause the video and try solving it. I'm going to read it real quick. So Teresa ran on a treadmill for 30 minutes and her time and speed is shown on the graph above. According to the graph, which of the following statements is not, it's nice that it uppercase capitalized everything for us, not. So we have to look for which one's not true concerning Teresa's run. So let's just go through each answer choice one by one and just check. Teresa ran at a constant speed. So the speed was the y-axis, right? So basically it's saying the y value was constant. Constant means same. Just interpret. So ran at constant speed. Ran at the same speed for 5 minutes. So where in here for 5 minutes is it a constant speed where the y-axis, where the y value doesn't change. Right here, right? This is for 5 minutes to 10 minutes. So that's 5 minutes total where there was a constant speed. The y value did not change. So A is correct, right? What I mean by that, it's true. Okay, that doesn't mean it's not the correct answer. It's true. Right? We need to find which one's not true. So it's not A, basically. Okay. And read B. Teresa's speed was increasing for a longer period of time than it was decreasing. So speed increasing, the y value increasing. So we just add up all, because it's increasing at different places, right? So let's add up all the times it's increased. So this time it add up increase for 5 minutes, right? From 0 to 5 it increased. So let's actually have Desmos keep track of this. So if there was 5 minutes of increasing, and then here there looks like it's 10 minutes decreasing, right? From 10 minutes to 20 minutes. So there's 10 minutes of decreasing, and there's another 5 minutes of increasing, and then there's another 5 minutes of decreasing. So you see that it increased for 10 minutes, but decreased for 15. So B is wrong because it says increasing for a longer period of time than it's decreasing. It's actually the opposite. It's actually decreasing for a longer time than it's increasing. B is wrong. So B is probably the answer, actually. But let's confirm. Okay, we read the other ones just to make absolutely sure B is right. Because if these are true as well, then we know for sure B is right. So C says Teresa's speed decreased at a constant rate during the last 5 minutes. So speed decreased. So speed has to be decreasing for the last 5 minutes. But what does constant rate mean? So we know the last 5 minutes, look at this, and it is decreasing. But what does constant rate mean? So whenever you see the word rate, this is really important. Okay, this is probably the hardest part about two-variable data questions, which is actually not that hard. It just goes to show you that they're pretty easy. Okay, but when it says rate, it's talking about the slope. Okay, when you see the word rate in a two-variable data question, or just in general, when you see like a graph, you see the word rate, it's talking about the slope. So what it's saying is that it's a constant slope. Okay, the slope is constant. Okay, so does the slope change? So hopefully you know what the slope is, right? In this case, the slope, at least how much it's changing, it does not, the change doesn't decrease. It's always changing at the same pace. Okay, it's not increasing or decreasing. If the slope was changing, then you look something like this, right? Because if you look at this, the slope it's really steep at first, and then it mellows out at the end here. Right? It's getting a lot less steep. Okay, this would be an example of a change in slope. Okay, this is a constant slope. You look at the slopes. Okay, the slope within this 5 minute period, that slope does not change at all. Okay, so the speed or the rate it's decreasing at is always the same during this 5 minute period. So when it says decrease at a constant rate, that is true. Okay, it is, the slope does not change. So it's basically saying Teresa's speed decreased, or the y value decreased at a constant slope during the last 5 minutes, which is true. Okay, hopefully that made sense. So C is true. Okay, so it's not the answer. Teresa's speed reached its maximum during the last 10 minutes. So the last 10 minutes, look at that. It reached its max. Yeah, it had its highest speed ever within the last 10 minutes. So that's true too. So the answer has to be B then. That's the only one that was definitely false. And we eliminated the other answer choices for sure. Last one. Okay, let's solve this one. I would prefer if you pause the video and try it for yourself. See if you can solve it. Okay, this technically is the hardest two-variable data question I've ever seen. But it's not that hard, you know. Because two-variable data questions aren't going to be that hard. Okay, but I'm going to try to solve it. So if you can solve this, you for sure set for two-variable data questions. Even not, as long as you understand it, I think you'll be fine. Hopefully you pause the video and had a chance to solve it. Let's read it. So 2 samples of water of equal mass are heated to 60 degrees Celsius. One sample is poured into an insulated container and the other sample is poured into a non-insulated container. Okay, the samples are then left for 70 minutes to cool in a room having a temperature. Okay, so they put both waters at the same temperature. They put them in 2 different containers. One of them is insulated, one of them is not. And then they just let it sit and then they measure the temperatures. Okay, they showed the sample of 10-minute intervals. Okay, so every 10 minutes they measure the temperature of both containers. Which of the following statements correctly compares the average rates? So when it says average rates, or it says rates, that's talking about the slope. So we're looking at the slopes. It compares the slopes at which the temperatures of the 2 samples change. So let's just look at it and just like get an idea of the differences between the slopes. So I think what helps is like you just draw these mini slopes just to give you an idea of what's happening with the slope. You see here, the slope is it does change a bit, I think. I think it does like mellow out a bit. Like the slope is slightly steeper here than it is here, but it's relatively the same compared to the non-insulated one for like the dots, the circle ones. The slope is really steep here, right, at the beginning, at least compared to here, right? The slope is definitely way steeper here, but then it becomes closer to zero. Like the slope is becoming flat, it's closer to zero. And the slope is not getting steep. It's pretty much flat by the time it gets to here. I think that's really it, right? This slope tends to vary more. It's at the beginning it's more steeper, and then here it's less steep. But this one's more constant. So let's look at the answer choices and check which one's correct. In every answer choice A says in every 10-minute interval, the magnitude means size. Okay, the size of the rate of change. Rate of change means slope, right? Rate means slope. So the size of the slope of temperature of the insulated is the square. Okay, the insulated sample is greater than that of the non-insulated sample. So it's saying at every single 10-minute interval, right? Every single x value, the y value for the box one, the square one is greater, which is completely false because like really right here, the magnitude, right? Magnitude is the size of the slope. Like this slope, it's decreasing a lot more. It's definitely bigger. Like if you were to get the slope from here to here, that number will be bigger than this one for sure. Like you can literally see it's decreasing a lot more than this one. So the rate of change is greater, or the magnitude is greater right there. So that's one. And also right here, the magnitude for this one is smaller than this one. So the circle tends to be bigger, and then it flips. Right, the circle's magnitude is bigger here, while the square magnitude is bigger here. So I think B was saying something the opposite of that, right? Saying the non-insulated was greater at all times, which is false because they flip, right? The one that's greater flips. So we know A and B are wrong for sure. Let's read C. Okay. In the intervals from 0 to 10 and from 10 to 20, the rates of change of temperature of the insulated sample are of greater magnitude. Insulated sample are of no, it's false, right? It's saying at the start from 0 to 10 and 10 to 20, the box ones are greater. That's false, right? It's the other way around. It should be the circles is greater at the start. So that's not right. Let's read D. In the intervals from 0, yeah, same thing. So at the start, the rate of change the temperature of the non-insulated, so the circle ones, which is true, are of greater magnitude. So greater magnitude, greater size, right? The bigger numbers, the slopes are bigger. Whereas in the intervals from 40 to 50 and from 50 to 60, rate of change the temperature of the insulated sample are of greater. So yeah, so that's exactly what I said earlier, right? It flips. So at the start, the slopes are bigger here, right? It's decreasing more. Like the magnitude is bigger here at the start. But at the end, it's actually the other way around. The slopes are bigger for the insulated ones, not the insulated ones, so flips. So the answer for this question is D for sure. Let's go over how to solve converting unit questions on the SAT. And converting unit questions are any time the question gives you a unit or gives you a bunch of units and asks you to go from one unit to another unit. In this case, it asks for how many acres could 48 ounces. So you can go from ounces of graphene to acres. So questions like this. And yeah, like you usually see like units being defined, like what equals what, things like that. And you'd be surprised, you can actually solve lots of questions that don't even seem like the converting unit questions if you know converting units really well. And the key behind all these questions is knowing how to set up fractions to cancel out the units that you don't want. Okay, I'm going to solve this question first, and then I'm going to have you solve this question, pause the video for that one. And we'll go over both. But let's go over this question first. I'm going to write out like all the units, what each unit equals what in numerical form. But normally like on the actual test, I wouldn't do this because I already know it. But I'm going to write that just so it helps you understand. So let's read this question. Graphene, which is used to manufacture integrated circuits, is so thin that a sheet weighing 1 ounce can cover up to 7. So we have a unit conversion for us right there. 1 ounce equals 7. I'm going to use FF for football fields. And OZ is going to be ounces. If a football field has approximately this acre, so that's another converting unit. So 1 football field equals an area of approximately 1/3 acres. Oh, and by the way, something cool in Desmos, which I don't think I've ever taught you, was if you type 1 and you type a space, you can actually do mixed fractions like this. Like, see, right, if there's a fraction, it's 4/3 actually. Like, this is the value of 4/3, which is interesting. I didn't know, like, you just type a space. If you type in 1 and then try to 1, like, that won't work. But if you type a 1 in a space, and then you type a fraction, it's apparently a mixed fraction now. I could do, wait, I want to see if I can do, like, times 3. Oh, yeah, that works. Yeah, it's a mixed fraction now. Okay, cool. And just in case, it's really rare that you actually see mixed fractions like this, but in case you want to type it in, that's how you do it. You just put a space. Okay. About how many acres could... Okay, so these are the units conversions, and we need to go from ounces, 48 ounces to acres, right? So we have 48 ounces, and we need to go from that to acres. So first of all, I like setting up fractions, and this is, by the way, this is how you should solve every single converting unit questions, is this. And lots of people make silly mistakes because they try to do it in their head, and they don't actually write out the fractions, but they like accidentally multiply or something, or like they do it in their head wrong, they accidentally divide instead of multiply, something like that. I would always, on scratch paper, when you're taking the test, just write them out real quick. It doesn't take that long. Just like make sure the units actually cancel out. And what I mean by units canceling out, I'll show you. So 48 ounces, 48 ounces of graphing. We need to go from this to acres, like something in acres, right? How do we do that? So right now we're 48 ounces. How can we go from acres? So let's define the path, okay? We have ounces. If we have ounces, we can go from ounces to football fields. And once we have football fields, we can go from football fields to acres. Let's go from ounces to football fields. We don't want ounces, by the way. We want to get rid of ounces. We need acres in the numerator at the top here, because it's like something in acres, right? So what you do is you actually always multiply by this fraction. This is a fraction, right? I'm going to show you. So I'm actually going to multiply this by 7 FF over 1 ounce. And what that does is it cancels out ounces, right? Because if the ounces in the numerator, ounces in the denominator, these two cancel out with each other once you multiply them, and then we're going to be left with football fields. Hopefully that makes sense. Basically, what we're doing, we're actually just multiplying by 1, right? Because we know 7 football fields equals 1 ounce, and if you have a numerator and denominator with the same value, it's going to equal 1, right? So basically, we're just multiplying by 1 here. So that's not going to change the value or anything. All it's going to do is going to convert to units. It's going to go from ounces to football fields now. Hope it makes sense. So you always multiply by, so once you make all these, once you identify like what equals what, then you just multiply them to like what you have until you get to what you want. And your goal is to try to cancel out difference. So if you have ounces in the numerator, you want, when you multiply this fraction, how do you know which to put in the numerator? Do you put football fields or ounces in the numerator? You should put ounces in the denominator. So that cancels out the ounces in the numerator. Right? Same thing here. So what do you think we should do? Should we put football fields in the numerator or acres in the numerator? The answer is acres in the numerator, right? Because we want to get rid of football fields. Because right now within football fields, we cancel out the ounces. When it's football fields, we don't want football fields. We want acres, right? So let's cancel out football fields by putting football fields in the denominator, so it cancels out with the numerator one. And again, you always just like turn these into fractions. Like this, it's always 1 on top of the other, or like this on top of that numerator denominator, and just multiply by that. So what you have to multiply this version, but in fraction form. Okay. So turn this into fraction form. Let's put times 1/3 acres, right? Oh shoot, it's not letting me. Okay, let me highlight it, and then there you go. And then 1 football field. So what this does is it cancels out football fields. So now ounces are canceled out, and football fields are canceled out. So all we're left is acres now, and then we can just multiply across. Right, so once all the units are canceled out, it's going to be in acres. So let's just do 48 over 1 times 7, no, times 7 over 1 times 1/3 over 1. Right, answer is 448. And the question asks how about how many acres? So the answer is C. By the way, if it's multiple choice like this, and you didn't get the exact answer, you messed up. You did something wrong. Unless the question actually asks you to estimate. This question actually tells you you need to round it. It says about, right? If it didn't say about, it says how many acres. You actually have to get the exact number. If you don't get the exact number, you got the question wrong. You can't round ever on the SAT, unless it actually tells you you're supposed to round. Okay, but the answer is C for this one. Hopefully that my explanation made sense for this. So first of all, I identify all the converting units, the conversions, and then I first go get what I have. So right now we have 48 ounces, and we go from acres. How do we make that happen? We just have to multiply by a bunch of fractions, and you set up the fractions in a way so that they cancel out the units until you get the units you want. And these fractions are basically just like these, but in fraction form. You just put one of them in the numerator, one in the denominator. How do you know which one to put in the numerator and denominator? You do it based on what you have to cancel out. So if ounces in the numerator, you want to get rid of the numerator and ounces, you just put ounces in the denominator to cancel those out. Hopefully this is making sense. We'll do more of these questions. I think you'll understand better. So try solving this question. Pause the video. Try solving this small private chat question. Okay, hopefully you solved it by now. Let's do it. So again, let's first identify all the converting units we're trying to make, right? So let's first read it actually. A small private jet is capable of flying non-stop for approximately 3,600 miles. Okay. So we have, let's just check that out. 3,600 miles. Let's do that. If the jet's average speed is 150 kilometers per hour. Okay. So 150 kilometers. That means kilometers per every 1 hour. Right, so that's another thing we have. How many hours can the jet? Or by the way, you can write it out. Cause that's I already told you the factor form, but you could just write this out as in 1 hour like this. That works too. But yeah, okay. Anyways, how many hours could the jet fly without stopping? Okay, so what are we trying to do? We're trying to go from. Well, we know for sure we're trying to get to hours. Like our final answer should be in hours, and I think we're trying to go from miles to hours. Yeah. Because we have miles right now. Let's go from miles to hours. How we do that? We can convert all of them. We have another thing too, because we have in miles. We need the kilometer equivalency, and it tells us that 1 kilometer equals 0.62. And also, by the way, it tells you the round, right? Too. It tells you the round the answer. So if you get like a really long number, it should be correct either way. Okay, 1 kilometer is 0.62 miles. So let's type that too. 1 kilometer equals 0.62 miles. Okay. So we have miles, 360 miles. And I just put a 1 here, so it's a fraction form. It doesn't really matter. But I have this. We have miles. And then we need to multiply. First, let's get to kilometers. And then once we have kilometers, we can get to hours, right? Because kilometers equals hours. So let's first multiply by this fraction so that we can go from miles to kilometer. What should we put in the numerator? We should put kilometers. I feel like Dora. I'm just like, where's the map? And then you guys answer it. Okay. Anyways, let's do this. And then 0.62 miles. And then that's going to cancel out the miles, right? And then kilometers is going to be in the numerator. So now we have kilometers. We need to go from hours. And that's going to be our final answer, right? So let's just multiply that. So we put kilometers in the denominator to cancel out the kilometers in the numerator. Let's do that. 1 hour equals 150 km. And now it's going to be in hours, right? This is going to equal hours because everything else is going to cancel out. The miles are going to cancel out. The kilometers are going to cancel out. All that's left is hours. So we successfully went from miles to hours. Now we just multiply across. Okay, let's just type that into Desmos times 0.62. And again, like why this works is because we're just multiplying by 1. Okay, we know this equals that. So we're just multiplying by the number 1 every time. So it's not actually like changing the value. We're just changing the converting units, which I think I already said, but hopefully it makes more sense now that you like actually understand it. Okay. Yeah, so that's the answer. And we've got the nearest 10th, and this is like 10th means the right after the decimal point, right? So it'll be 38.7 would be the answer. Hopefully I didn't mess that up because I don't actually have an answer key. Okay, hopefully you got the same answer as me. Let's move on. Now let's talk about converting radians and degrees because they do test you on this. Now you notice it doesn't tell you, like it should always tell you, by the way. In converting unit questions, it should always tell you the converting differences, like how to convert from one thing. The only time where it doesn't tell you stuff is radians to degrees. Like I mean, it doesn't tell you like the conversion like this. It doesn't give you this type of thing. The only time it doesn't give you that is radians to degrees or any time units, like hours, like how many minutes are in an hour, how many seconds are in a minute. You should already know that. So I think that's why it doesn't give it to you. But any other time that you're trying to convert between units, it should always tell you what the conversion is. Okay. But it does tell you what radians to degree is. If you go in the SAT formula sheet, SAT reference sheet, I'll just switch it up. But like this is obviously built into the software too. Right next to the calculator button, to the right of it, you can press that, and you'll see this. And you notice here it says the number of degrees of arc in a circle is 360, and the number of radians of arc in the circle is 2 pi. That's basically telling you 360 equals 2 pi. Right? Because they're the same thing. They're both the number of degrees in a circle, and if that equals to 360 as well as 2 pi radians, that means 360 equals 2 pi. So that's your conversion. You can just do 360 equals 2 pi. And that's how you can set up the conversion between radians and degrees. So you don't actually have to memorize it. There's no memorization of that needed. You just need to look at the formula sheet, look at the bottom, and it tells you the conversion between the two. So let's write that actually. 2 pi radians. Let's do let's do, radians. So let's type it out. 2 pi radians, that equals 360 degrees. Okay, so we have that. Now let's convert. So the number of radians, we're trying to go from degrees. We have 720 degrees. 720 degrees, and we're trying to go from that to radians, right? It's asking what the value of A is, and this is like the number of radians, A pi. So we're trying to find what A is. So we just need to go from degrees to radians, and then we can find A. Okay, let's do that. So obviously we have this. Let me do that. Okay, 720 degrees. When we multiply by this fraction, what do we put in the numerator and denominator? We put degrees in the denominator to cancel out degrees in the numerator. So let's do 2 pi radians, and then put degrees, 360 degrees in the denominator. So those cancel out, and then we're left with radians now. That's going to equal radians, which is what we want. Okay. By the way, if you don't know radians, this is a measure of angle. If you didn't learn that, if you didn't take pre-calc or something, radians is like the same thing as degrees. There's just like measures. It's like another unit for measuring angles. Okay. Let's multiply this out. 720 degrees, 720 over 1 times 2 pi over 360. You could just not type pi and this would be the answer. But if you didn't do that, you could do this, and then this would equals A pi, right? So you could just do total A pi and then look at what A equals. That works too. Either way, but the answer is 4 for sure. Okay, hopefully that made sense. That's converting radians to degrees. And you know the conversion, just look at the reference sheet. Okay, let's talk about a really common mistake people make. You have to watch out for this. There's a difference between cubic centimeters and just centimeters by itself. Same thing as like square centimeters. Okay, those are different units, right? If it says centimeters, you have to make sure it's actually cubic centimeters before you use it in the fraction. So I'll try solving this. Actually, pause the video, try solving question 16. Hopefully you solved it by now. I'm going to solve this now. Okay. As the size of a fireworks shell increases, the height above the ground... So it's probably going to convert from like size of the shell to height, maybe, of the ground when the firework burst increases. Okay. For a firework to burst this amount feet above the ground, a firework shell in the shape of a sphere could be with this. Okay. What is the volume of the... Okay, wait. Why is this? I'm so confused. So okay. So we have cubic inches. I think this is just useless. Like, this doesn't matter. We're just trying to go from this number. It looks like we're trying to go from volume to volume, right? So the feet doesn't matter at all. All we need to do is just go from cubic inches to cubic centimeters. Okay, let's make that happen. So 5 or 2.68. And SAT do throw like numbers that actually don't matter. It's kind of rare when they do that. I'm kind of surprised. Usually they don't do it. Usually every number matters. But for this case, I'm pretty sure it doesn't. Because it's really... What we need to find the volume. It already gives us the volume, and it's asking for the volume. So all we need to do is convert from volume to volume. We don't need to worry about feet. Okay. That is cubic centimeters could be used. So cubic centimeters, okay? That means centimeter. Wait, yeah, inches. Okay, we have inches, my bad. So 54268 inches cubed. Okay. That's different from just inches by itself without cubed, by the way. And we know the conversion. It tells us 1 inch equals 2.54 centimeters. So 1 inch equals 2.54 centimeters. Okay. And we're trying to convert between the two. So let's take this. We have this, and we're trying to go from this to cubic centimeters. So centimeters cubed. Okay. We cannot just do this. If this is what you did, you got the question wrong. You can't just do 2.54. You can't do that. Like, this wouldn't work. Why? Because you're not fully converting between the two. Basically, now, you notice how this 3 up here is only going to cancel out with one of this. This is, by the way, when you cube something, it's basically just saying inches times inches times inches. Right? So there's actually like 3 inches here. So when you multiply by this, you're only canceling out one of the inches. You're not canceling out all 3 of them. So you need to multiply this 3 times. Okay? To do times this and times. You need to do it 3 times over in order to actually convert. between inches. That way, there's 3 inches that cancel out the 3 inches in the numerator. You can also shorten this to just let me retype this actually. You could just shorten this to inches cubed, and then just cube both sides. Because like same thing here, right? This we can just transform this. If we want this in terms of cubic inches and cubic centimeters, let's just cube both sides. Because whatever you do to one side, the other side, if you do the same thing to the other side, it's gonna stay the same. So 1 inches cubed equals 2.54 centimeters cubed, and that's the same. So we just use this instead. Oh my bad. Wait. Be really careful. You have to cube this too. You have to cube. I would cube 2.54 centimeters. Because if you cube everything, you cube everything here. And obviously, 1 cubed is just 1, so you could do that too, but it doesn't matter. So we're just cubing every single thing. You could think of it as like parentheses, and then you cube it. It's the same thing; they're equivalent. Okay, so we cube everything, and then we can convert it. So instead of doing this, we could also just do this cubed, right? We cube both sides. We're just using this fraction now instead of the other one, and then this is 1. Obviously, you can do this. And now this inches cubed, we cancel out this. And then we actually be in centimeters cubed too, which is what we're trying to get to. And same thing here, by the way. We get centimeters cubed because there's 3 centimeters here. Okay, so let's multiply that out. 542.68 over 1 times 2.54 cubed over 1. And yeah, inches in the denominator, cancel those out. And that would be the answer, which is that number. That it's a really big number, but 889. Are we trying to round? Oh, to the nearest whole number. What is the volume? Yeah, so it's probably just 8893. That's the answer. And hopefully that's what you got. And again, remember if it's squared, by the way, then you square it instead of cube it. You just use 2. Right? If the question said centimeters squared or squared centimeters, right? Then you just use square it with the 2 on top instead of 3. Okay, but if you multiply this out, it's also the same thing. You get the same answer. Hopefully that makes sense. A really common mistake is people forget that. There's a difference between cubed and squared versus just without cubed or squared. Okay, so make sure you keep that into account. Okay, let's talk about more questions that don't actually seem like the converting unit questions, but they actually are. Let's talk about density. Okay, density, they show up like a decent amount. They talk about density a lot. You don't even need to know the density formula. Like a lot of tutors, they teach the density formula. You have to memorize this. You don't need to know it. You could just pay attention to the units, right? Just like cancel out the units and get to what you're trying to get. So, density of a certain type of wood is... Actually, pause this video and try solving it. I keep on forgetting. Pause the video, try solving it. Hopefully solved it by now. Now I'm going to solve it. Okay. Density of a certain type of wood is 353 cubic kilograms. So let's write that down. 353 kilograms equals 1 cubic meter. So meters cubed. Okay. A sample of this type of wood is in the shape of a cube and has a mass of this amount. So mass of 345 kilograms. That means mass is just 345. So I guess that's what we're starting out with, and we need to convert it to the nearest hundredths of a meter. What is the length of one edge of this cube? Okay. Cool. Yeah, so we're just trying to go from kilograms to meters. That's it. Let's do that. And we can just multiply this, right? Just do this, and then we want to cancel out the kilograms. So we would do 1 meter cubed over 353 kilograms. That cancels out the kilograms. The problem right now is we're trying to get to meter, not cubic meter, right? So to hundreds of a meter. So I feel like we would have to cube root this afterwards. So let's try that. So first of all, I don't think I've ever done this question actually. I don't remember this question at all. 345 times 1 over 353. Alright, so that's in, what do you call it? That's the meters cubed. So right now we're in meters cubed. But we want to get to just meters by itself. So right now this is meters cubed. Let's get rid of the cubed by cube rooting it. So we do CBRT, cube root it, and then just put that in there. So that's going to cancel out obviously if you cube root this entire thing, it's going to cancel out, this 3 is going to cancel out with this 3, right? So it's going to make it just in meters. So let's do that. And that should be the answer. So the answer is actually B. Yeah, so be careful. If you got, this is why in the pay attention, this is why like I always like draw out this. Like I always like write it out. Because if you do it in your head, you probably wouldn't notice that. The answer for this one is actually B, because you need to go from meters cubed to regular meters as well. Don't forget that. Last question, let's talk about this. Notice when you first look at this question, somebody not experienced on the SAT, they probably wouldn't even think about units. Honestly, they would try to like reason through this. But here's a huge hack for questions like this. If you see word problems, there's equations like this, which are actually pretty common, and there's a bunch of units in the question, you don't even have to think for these questions. You can just try to cancel out the units, and that's pretty much just going to give you the answer. At least it'll tell you, like, it'll help you eliminate a bunch of definitely incorrect answer choices if you do questions like this. So pause the video. This is actually a pretty hard question. So pause the video, try solving this, see if you can do it. Okay, hopefully you have time to solve it. I'm going to solve this now. So let's do this. Alan drives an average of 100 miles each week. Okay, his car is traveling on average 25 miles per gallon. So that's probably a unit that's important. We could type in 100 miles. I actually don't think this is going to be important. Just because I kind of vaguely remember this question. But we can write that down too. Okay, has an average of 25 miles per gallon. So 25 miles equals 1 gallon. That's what that's saying. Alan would like to reduce his weekly expenditure on gasoline by $5. Okay. There's a bunch of units here, $5. Assuming gasoline costs $4 per gallon. So that's another. So $4 equals 1 gallon. Which equation can Alan use to determine how many fewer average miles he should drive each week? Okay. This is tricky. Let's first look at the answer choices here, and let's make sense of the units. Let's first pay attention to like the 25, 4, and the M. Wait, because M, by the way, M is average miles, right? So 25 is in miles per gallon. Let's write that down. 25 miles per 1 gallon. Okay, so that's the 25 on top. And the 4 at the bottom, I'm just looking at A and B for some reason. We'll just go with that. We'll see if it's the right one. So 4 is dollars per gallon. Right, so $4 per gallon. Okay. And miles is average miles. So miles average M mile. I'm gonna type in that stands for M miles. Okay. And what would this equal? If we were to multiply this out, like what if we try to cancel all of the units, what would this equal? So the gallons here would cancel out, right? Because yeah, like you can do like because this. Okay, wait, let me show you. 25 miles. Like if you don't know this, you could, it's basic math wise, if you dividing fractions, you flip the fraction in the denominator. I think it's keep change flip. I think that's what it was. Keep change flip. So you keep the first thing, and then you change from division to multiplication. So you change the operations you're using, and then flip the bottom one. So gallons, and you can search this up. Honestly, like this is just basic middle school stuff, but it's okay if you don't know it. But now you know, all right? So you can cancel out. So this is equivalent to this, and we cancel out the gallons. The gallons will cancel out. So this is actually in 25 miles. And $4. And then we're multiplying by this, right? So miles, yeah. Okay, so this would actually, the units of this would be miles squared over $4, right? Because these miles will multiply. This is just the miles in the numerator, right? You could just, wait, it's not, what the heck? Wait. Yeah, okay. So you're multiplying these two, and it would just give you miles squared over dollars, right? That's not the units we're trying to get to. Like, if it's either 95 or 5 is in dollars, right? And 95, I don't even know what 95 is. Like 100, but that's in miles. So I feel like 95 is just wrong, because where would 95 come from? You have to do, I see why a lot of people pick 95, because you think 100 minus 5, and you could do that. But 100 is in miles each week, and so it's in miles, and then 5 is in dollars. You can't subtract the two because they're different units. So it's probably just going to be 5. And honestly, we're saying how many fewer average miles. So we're looking at how much it decreased by, not how much is left after you decrease it by. Hopefully that makes sense. So I think a lot of you would pick 95 because you're trying to get how much is left after you decrease, right? After the decrease, how much is left? So the $5 you subtract it from 100, and that's how much is left, right? But that's actually not the case. Even if you didn't realize the units were wrong, because you can't subtract dollars from miles, but you're trying to get how much is actually, how many fewer miles, so the actual decrease amount, not how much is left after you decrease. So you're just trying to get the 5, which is the reducing amount, which is what they're reducing by. So it's how much fewer is left. Hopefully that makes sense. So like that's why you're using 5 instead. And either way, the units are definitely just like they don't make sense. So like 95, like where would you get 95 from, right? So it probably is 5. So 25 on top of the 4 didn't make sense. Let's do 4 on top of the 25. Let's try that out. So oh, this is such a pain. Okay, I'll just copy and paste this and you'll see. But by the way, you should be doing this on paper. I'm just doing this on Desmos because why not? But like you should be doing this on paper. It's way faster than paper. Okay. I'll do this, and now let's multiply this out. So this would actually equal 4 over 25 miles times miles times this, right? And you see the miles cancel out, right? So this is actually, the units of this is actually going to be in dollars, which is what we're trying to get to, because the 5 is in dollars, right? So the answer is just D. Hopefully that makes sense. How we solved this problem, we didn't even have to reason. I bet you most of you, if you didn't know converting units, you would try solving this question just by reasoning it through. Like if I have 4 over 25, what's that gonna do? How's that gonna relate to 5? And then you try to like reason out a bunch of things. You don't even have to think. Like I pretty much, there's no like thinking involved. I just read all the units and it's like plug and play, and then, oh, the units cancel out here. That unit's correct, so it must be D. Like that's pretty much it. Hopefully that makes sense, because we're trying to match the units on the left side of the equal sign to the units on the right side of the equal sign. And D is the only one that makes sense. Like 95, what is that? Like 95, the units for that is crazy. It's like 100 miles. It's in miles minus dollar. Like what unit is that? Right? So that wouldn't make sense. So 5 is definitely just the dollars. So we're trying to get dollars, and this side equals dollars too. If you cancel out all the units involved, that equals dollars. So D is the only one with dollars equals dollars. So that's going to be the answer. So if you see questions like this, play around to units. I will say sometimes you can't actually get the answer right away from the units. Like maybe there'll be 2 that have the units correct, and then you just use reasoning. Like maybe like 95 wouldn't make sense. You're trying to get how much fewer, so you're trying to get the decrease. And you're not trying to get how much is left after the decrease, and you can like reason out for that. But most of the time, you can actually just get the answer just from units minus units. So if you see word problems like this with crazy units, and then there's answer choices is in equations or like some kind of expression stuff, you could just try to cancel out the units. Like get all the units for each number, and then like see what the units equal, and just like make sure the units match. Okay, cool. So that's converting unit questions. And again, all of these is just first identify all the conversions, and then go from what you have. So in this case, we had 48 ounces, right? And we try to get from ounces to acres. So go from the unit you have and multiply in fraction form with all the converting units you have, and you have to figure out what should be the numerator, what's in the denominator by trying to cancel out different units, and eventually you'll get to the unit you're trying to get to. And just watch out for cubic and square stuff, but it's pretty straightforward. I would always just write it out on scratch paper, just in case you make a mistake with like you accidentally divide the multiply if you try and do this in your head. Just to completely reduce the mistakes, I would just write it out real quick. Okay, that's it. We are officially halfway done problem solving data analysis, and up next is percent questions. Now, percent questions are the type of questions that students struggle with the most, in my opinion, in problem solving and data analysis. So this is a pretty important section. However, I've already made a YouTube video about percents, and since I don't have anything new to add to that video, I'm just going to play that video right now. So you're just going to see this video. So if you already watched this YouTube video, this percent YouTube video, I'll put it on the screen right now. So if you already watched this specific video, you can just skip ahead to probability. I'll put chapters in the video, so you can just click on the scrolly thing to probability. The section that has probability, and you can skip right to probability. I mean, you can watch the percent video again if you want to, but I'm just saying it's going to be the exact same video. So I'm about to play that percent video right now. In case you didn't know, on Desmos, which is the calculator built into the SAT testing software, you can type in percents. For example, I can type in 50% of 6. It's automatically going to do the calculations for me. I can type in 75% of 2. It's automatically going to give me the answer. And by the way, to type in the percent of, all I'm doing is pressing the percent symbol on my keyboard. I'm literally pressing Shift 5 on my laptop, and it's automatically going to put the of right next to the percent for me. But because of this, you don't even need to know how to convert between a decimal and a percent. You definitely don't even need to. However, I'm going to teach it to you anyways because it's important to know as a high schooler, and also it could save you in a pinch. You never know. So 50% of 6 is the exact same thing as 0.5 times 6, or half of 6, right? And 75% of 2 is also the exact same thing as 0.75 times 2. Okay, the difference between a percent and a normal number or a decimal is a factor of 100. So to convert between the normal number to a percentage, you have to multiply by 100, right? Because 0.5 times 100 is 50. So 50%, right? So converting between a normal number to a percentage, you multiply by 100. And to convert between a percentage to a normal number, you have to divide by 100, right? So if I have 50% and I want to go back to a normal number, I have to divide by 100 to get 0.5 back again. This also means, obviously, then that 1 is the same thing as 100%, right? 1 times something is the same thing as 100% of that something, okay? And also, let's do a slightly harder thing. Let's do 1.2345. Let's say this is a normal number, and I want to convert this to a percent. What do I have to do? Okay, you have to multiply by 100, right? So 1.2345 times 100, that's the percent. So this is actually 123.45%. Okay, now that we got that out of the way, let's do our first practice question. And these practice questions will get progressively harder as the video goes on. Okay, so first thing, try pausing the video and solving this. Hopefully you had a chance to try solving this question. Now, I'm willing to bet most of you got this question wrong, actually. Most of you did something along the lines of 500% of 5, or 5 times 5, and you got 25. That's actually wrong. The answer is actually 30. Okay, the reason being is because this 500% is just the amount it increased by, right? It says the result of increasing the quantity 5 by 500% is x. So we need to get the amount after the increase. We don't care about just the amount that it increased by. Okay, so we have to take the original amount, which is 5, and you add on the amount that it increased by, and then you get the resulting number, which is 30. Just to rephrase that, because it's really important that you understand this. This is a super common trick that the SAT uses over and over again that you need to know to look out for. Okay, the result of increasing the quantity 5 by 500%. So because it says the result of increasing the quantity 5 by 500%, that means 500% is just the amount that this number increased by. Okay, so this is the amount it increased by. That's not the resulting number. That's not what x is. Okay, that's just how much you increased 5 by to get to x. Because you still have to take the original number and you add on the amount increased by to get the resulting number. And it's also important to understand that 5 plus 500% of 5 is the exact same thing as 600% of 5. Okay, this is just to convert between the two. I guess to simplify it. Okay, it's helpful to know this, right? Because 5 is just 100% of the number, right? Like what is 5? 5 is 100% of 5, right? So it's really just 100% plus 500% of 5. That's going to be what the answer is equal to, right? So you take the original 100%, or the original number, and you increase it by 500%. So you take the original number, which is 100% of the number, you increase it by 500% of that number. So this is 100% plus 500. That's going to be 600% total, right? So 600% of 5 is the same thing as 5 plus 500% of 5. Okay, and by the way, it could also be decreasing, not just increasing. If it said, for example, the question said the result of decreasing 5 by 20% is x, and then it asks us like, what is x, right? If you solve this, then you would have to, you can't just do 20% of 5, right? That's wrong. Okay, because this is the amount decreased by. So you take the original number, which is 5, and you decrease it by 20%. So 5 minus 20% 5, and it's 4. And hopefully it makes sense to you now that 5 minus 20% of 5 is the exact same thing as 80% of 5. Okay, because remember, this 5 is just 100% of the number, right? So 100% minus the amount decreased by. So the original number, which is just 100% of that number, right? We didn't do anything to the number yet. So 100% of that number minus 20%, so decreased by 20%. So the amount of percentage that's left after you decrease the original number by 20% is 80%. Right? 100 minus 20 is 80%. So basically decreasing by 20% is the exact same thing as 80% of that number. Okay, same thing. Increasing by 500% is the same thing as 600% of that number. And I would rewatch that portion if it didn't make sense to you, because it's really important that you do understand it. Okay, but overall takeaway, you have to be really careful when it says increasing or decreasing by something. Okay, if it just asks for a straight up percentage, like what is 500% of 5, then you could just do 500% of 5. Okay, if it just asks for a straight up percentage. But if you see something that signifies increasing by or greater than, if it says like this percent greater than this percent, something to do with like increasing by or decreasing by, anything that signifies that, you have to take into account it's the original number plus or minus the amount that's increasing or decreasing by to get the resulting number. That's super important. Okay, they test that a lot. So whenever I see a percentage, by the way, I always look out for that. Like the first thing on top of my mind when I see percentage in the question, I always check if that percent increasing by, decreasing by, or just a straight up percentage. Like what is this percentage of that? Okay, let's do the next question, which should be slightly harder than the previous one, at least for most people. Okay, so pause the video and try solving question 12 here. Okay, question 12 says a customer paid $53 for a jacket as a really expensive jacket after 6% sales tax was added. Okay, what was the price? So right away, I think a lot of you probably were like, oh, 53 after 6% sales tax was added. So let me just figure out what is 6% 53 and then subtract, right? Because it's asking for what is the price of the jacket before the sales tax. So you're probably thinking, oh, I just need to subtract 6% off of 53, right? Because 6% of 53 is this number. Okay, so 53 minus that number, 49.82. No, that's not even one of the answer choices. You know you got the question wrong. You might go, oh, 50. By the way, if it doesn't say to round the answer, like this question never says round the answer to the nearest whole number, or to like what's the closest number to the answer, or something like that, then you know you got the question wrong if it's not exactly the same answer. Okay, but the reason why this is wrong is because you have to do the original number multiplied by the percentage equals the after number. It has to be that formula. Okay, it has to be, for example, like the original number, we don't know what the original number is. We need to find that number. But the original number plus or minus the 6%, right? In this case, it's plus the 6% because its sales tax was added. So the original number plus 6% of the number, that equals 53%. The resulting number of that is 53%. Okay, you see the answer is actually 50 here. But if you don't understand what I'm doing here, you should watch my Desmos guide. Okay, this is the squiggly line that automatically estimates the value of all the constants. So basically finds the value of x1 that makes both sides of the equal sign equal each other, or both sides of the squiggly line equal each other. And that's really important that you understand. That's I will watch my Desmos guide, which I'll have somewhere in the video. There'll be like a pop-up there that you should definitely watch. Okay, but it has to be, again, a number times the percentage, or in this case, again, this is the same thing as the original number times 6% or 106%, so 106% of the original number equals the resulting number. Okay, it has to follow this formula, right? The percentage of this number equals the resulting number, or this number times like the percentage equals the resulting number. It has to follow this format. And another way you can think about this is, what was the 6% on, right? The 6% was of the price of the jacket before the sales tax was added. So it's whatever X was, whatever the answer is. Okay, it's not 53. So you have to make sure that the 6% is always on the number that it's supposed to be on. Right, this is 6% is on the price of the jacket before the sales tax. So whatever that number is, we need to keep that 6% on that number. Okay, we can't automatically change the 6% to a different number. It doesn't work like that. Okay, you have to keep the percentage on the correct number. So in this case, 6% was on, in this case, X. So we have to make sure that 6% is always on X. You can't put 6% on a new number. Okay, this isn't the right number. You have to keep it on the original number. Okay, let's move on to the next question. And okay, these are just going to get harder and harder as we go on. Okay, so pause the video and try solving question 20. Hopefully you had a chance to solve this. Now this question says, Alma bought a laptop computer at a store that gave a 20% discount off its original price. Okay, so it doesn't tell us what the original price is, but let's say the original price is X. Sure. Okay. And we 20% discount off of. So that's saying 20% decreased by 20%. So that's the same thing as 0.8%. Right? So I'm just going to do times 0.8. Okay. Or you could think of it as the original number minus 20% off of that number as well. But again, this is equivalent to this. So I'm just typing in simplified form. Okay. The total amount she paid to the cashier was P dollars, including 8% sales tax on the. So it seems like with this, okay, this is the new number now, right? After the 20% discount, after the discounted price, this new number, there was an 8% sales tax on this number. So let's take this number. There's an 8% sales tax on this. Okay. So increase by 8%. That means, okay. And this equals P. So that's the equation actually. So notice this, it's still percentage times the number, right? This is the percentage. multiplied to a number equals the resulting number. And then there's a new percentage now. So there's a new percentage multiplied by a number equals the resulting number. Okay, and you notice we were very careful on what is the percent on, right? There's two percentages here, right? There's the 20% discount off of, and there's the 8% sales tax, right? The 20% discount off of was the original price, right? So we made sure to multiply the original price by the percent. But you can't do 0.8 times P. It doesn't work like that. Okay, the 20% is the discount off of the original price. And it doesn't tell us what the original price is, so I just did X. You could have put anything here, okay? It's just whatever the original price is, it's multiply it by the 20% discount off of, which is the same thing as 80% of, or 0.8, right? And the 8% sales tax was on the discounted price. So this is the discounted price, right? The discounted price is after the 20% discount. So the discounted price, and that's what the sales tax was on. So you have to multiply sales tax by the discounted price, because you have to pay attention to what the percent is on, and then make sure that percent is actually on that number. You can't just do 8% sales tax on P. It doesn't work like that. P is the amounts you pay to the guys, the final number after all the percentages are done. Okay. But it's very straightforward. It's just percentage times the number that it's the percent of, and then you just solve the question based on that. So it's just the percentage times the number is percent of, and the percentage times the number is percent of to get the final answer. Okay, so we need to get the answer though, right? It says which of the following represents the original price of the computer in terms of P. So basically, we need to isolate X, because that's the original number. Whereas like what does X equal in terms of P? So to get X by itself algebraically, you would have to divide 1.08 and divide the 0.8 to the other side, right? So it would just be X equals P over 0.8 times 1.08, because we divided these two numbers to the other side to get X by itself. So the answer is D here. Okay, what we've gone over so far is kind of like the basics of percents. Now let's go into like the actual common pattern to see, at least for the hard questions on the SAT. So pause the video and try solving this question. Okay, hopefully you had a chance to read it and at least get an idea of how to solve this. Now, it's kind of important. You need to watch the Desmos guide to really understand what I'm doing here. Okay, because this is a very common pattern. It's actually probably the most common percent pattern you'll see. Like half the time, there's always going to be at least one really hard percent question on the SAT, and half the time it's pretty much this type of question verbatim. It's like the exact same as this type of question. Maybe the numbers are different, maybe it words it slightly differently, but it's going to be the exact same. Usually the wording is actually really similar too. Okay, but when you see this type of pattern, you're going to have to do bracket regression. At least this is what I do to solve these questions, right? Because you think about there's three equations here. There's positive number A. A is 2,241% of the sum of B plus C. Right? So it's saying this equals 2,241% of B plus C. That's the first equation. Second equation is B is 83% of C. Very straightforward. B is 83% of C. And again, for any percent question, I'm super careful about making sure the question doesn't say increasing or decreasing by a percent. Okay, this is very straightforward because it literally is this percentage of a number. But if the question said the sum of the positive numbers increased by 2,241%, then that would be a completely different answer, right? Because then this would just be the amount increased by. You'd have to like add 100% to it to account for like the actual percentage. Or you could do like the original number plus this increased by amount. Okay, but it doesn't say that here, so we don't need to worry about that. But just make sure you check for it. Okay, B is 83% C, and then the final equation is what percent. So I'm just gonna put W for like what, right? So what percent of B is A? So it equals A. That is very straightforward. I actually go over a very similar question, or maybe this exact question on the Desmos guide. So you should watch that. Okay, but basically you just need to combine this pattern into the brackets. Okay, and you basically take the left side of all the equations, put them in the left bracket, separate them with commas, and take the right side of all the equations and put them in the right bracket, separate by commas. And I could go on and explain all the regression to you. So I would just watch the Desmos guide I have. It's the most popular video I have on my YouTube channel. There's also links to that somewhere in the video. Okay, you should watch that. Okay, so I put all the left side of the equations on the left bracket, and I'm putting the right side right now, 241% of B plus C. And this is just the most fastest and reliable way to solve these types of questions. By the way, C, that's why I'm doing this, is A. Right, and it tells you the answer. W equals 4,941, which is what we're trying to find. We're trying to find what percentage of B is A, right? In which case we just said W. Right, so what is W? And the answer is 4,941. The answer is D here. Okay, and it's just super important that you know this pattern really well because it's a common pattern that they ask over and over again. Okay, let's go to an even harder question though. This is question 22. Try solving this question. Pause the video, make sure you fully understand what's going on here, and then get at least an idea from start to end of how you're going to solve this question. Okay, so this question said, a researcher monitored 2 mite populations in a closed habitat. So basically, we're dealing with 2 populations here. So probably 2 numbers. Oh, it says a predator species and prey species. Okay, so 2 predator and prey it feeds on. At the start of the week, both populations were the same size. Okay, by the end of the week, prey population has increased by 4. So remember, it says increased by. So I'm always looking out for that one. It's a percent question. Increased by. Okay, so be careful. Okay, if you just did 400% or 4,000% of a number, that's wrong. You have to take into account that that's just the increased by amount. You have to add on the original number to the increased by number. Okay, increased by 4,000% of the prey at the start, and then the predator increased by 90% of the predators at the start. Okay, so they both start with P. I'm just gonna do X1 and X2. So X1 is gonna be the predator. Sure, predator is gonna be X1 because that's what came up first here. So predator species X1, and whenever you just have percentages and you don't really know what to do because it doesn't give you a number to work with. This is percentages only, and you don't know what to do from here. What I like doing is just making up a number for the starting number. So whatever the original number is, just make up a number for it. Okay, in this case, there's 2 original numbers, but they're the same number anyways, because it says they're the same size. So we could just say 100. I think I like using 100 because it's a really easy number to work with, but you can pick any number. Okay, I just like using 100, especially when working with percentages. Okay, so X equals 100, X2 equals, so okay, the predator population is 100 and the prey population is 100. Okay, I just put up a random number. I just like using 100. This way it's much easier to work with because now we actually have a number we can work with and just see what happens when we use that number, right? So by the end, the prey population increased by 4,000%. So the prey population, which was 100 or X2, increased by 400%. So again, the increase by means you take the original number and you add it to the amount that it increased by. So 4,000% of X2, that's going to be the resulting number. So by the end of the week, this is how much prey there was. Okay, and then the predator population increased by 900%. So predator, which is X1, you increase it by 900%. Okay, so that's and the answer would be 1,000. Okay, so after the end of the week, there's going to be 4,100 prey and then 1,000 predators. And the question says, at the end of the week, the prey population was P% greater than the predator population. Remember, P% greater than, right? So P% is the amount increased by. This is really tricky, okay? You might have caught the increase by here and increase by here, but you might have missed this part. This is super important. Okay, the P% is just the amount that we just need to find the amount it increased by, not what percentage of this is that. Okay, just the increased by percentage greater than the greater population. So how much greater was prey than predator? Now this is pretty much as hard as percent questions will get that you'll see on the SAT. So if you could solve this question, well, you understood how to solve this question, you made sure that if you solve a similar question to this, where there's just percentages or increased by percentages everywhere, and you know, okay, I just need to plug in a random number for the starting amounts and just see what happens. As long as you understand that, you'll be fine. You can solve every single percent question. Okay, so the 2 patterns I would really understand is just this. Again, be careful about increased by or decreased by percentages, and also be careful that you always multiply the percentage to the number that's actually supposed to be multiplied to. Okay, it's the 4,000% of the number of prey at the start of the week, at the start. So you only multiply it to the start. As long as you make sure that the percentage is on the number it's supposed to be on, and you pay attention to increase by, decrease by, you'll be fine. You can solve every single question. Also, if you see this type of pattern with like 3 different equations, like this number is this percentage of that, this number is this percentage of that, what percentage is this of that? If you see that type of wording, then you know, okay, bracket regression. I would highly recommend you watch the Desmos guide on how to solve, like how to just understand your bracket regression and the squiggly line, everything like that. but everything else should be very straightforward. Now let's solve a more unusual pattern that I have seen before, but not often, maybe like one time out of the past 10 months. So it's really rare that you'll see a question like this, but it's pretty hard. So in case you do see something like this, I want you to be prepared on how to solve questions like this. Okay, so pause the video, try solving this, and see if you can do it. This question says, how many liters of a 25% saline solution must be added to 3 liters of a 10% saline solution to obtain a 15% saline solution? So when you see questions like this, there's actually a formula for it. I think it's just easier for you to memorize this formula most of the time. So I'm just gonna have you do that. This is how you solve questions like this. So basically, whenever there's a question about different percentages of a solution, you have to mix two things together to get another percentage, where there's basically two solutions, right? This solution, they have differing percentages in them. You have to figure out how much the mix of each one to get the final percentage to be this number, okay, or like whatever number it tells you in the question. The concentration, which is just another word for the percent, right? So what's the percent, what's the concentration of this thing, times the amount, which is just the amount we're pouring in of this concentration. So how much are we pouring in to this big one, right? Plus the concentration, which is just the concentration of the other one, so 10% of the other one, times the amount we're pouring in. So this case is 3 liters, because it tells us 3 liters of a 10% saline solution. So it's just, we're pouring in 3 liters of this into the big thing, right? And then equals the concentration total. So the 15%, what the concentration we want to get is 15%, times the amount of this total, like how much is in here actually. Okay. So let's just plug in the numbers that we do know. All right, let's step in the formula and then plug in the numbers that we do know of this formula. So the percentage, we know all the percentages. It tells us all of that. So the concentration, we're at 25%, 25% of the amount. Or let's do in decimal form because that's what the formula is in, right? 25% times the amount, which we don't know. We need to find that. That's actually the answer that we're trying to find. We need to find how much we're pouring of this to get everything else, right? So this, we don't know that, plus the concentration, which we do know for the other one, 10%, or is 0.1, is 10% times 3, which we do know, right? We know how much we're pouring in of the 10% solution, equals the concentration total, which we know is 15%. So all of this should result in a 15% concentration times the total amount. Now, we don't know what the total amount is, but we do know that this total amount is just the result of pouring this into this, or pouring both of these in, which you already know how much we're pouring into this one. We just need to find this one. Basically, it's just the amount we pour in plus the amount we pour in. That's it. So it's really just the amount we pour in plus the amount we pour in. So we already know how much we're pouring in for the 10%. We need to find what it is for the 25%, but we know like this, the result, this final bucket here is just going to be the addition, the sum of how much you pour in for both of them. So that's going to be the total amount. And then we can just have Desmos solve for this, right? Because there's only one variable. Desmos can solve for this easily. Let's replace the equal sign with square root line. Tell Desmos to find the value of the constants that makes both sides equal each other. In this case, it's just find the value of x that makes both sides equal each other. And the answer is 1.5 for this question. Okay, and again, the main pattern for percents is going to be this. Like, this is really common. The SAT loves throwing in these types of patterns. And also, just know worst case scenario, as long as you know that the percentage has to be on the number it's the percent of, and you know to pay attention to increased by or decreased by amounts, then you'll be fine. And you can just plug in random numbers for the starting number and just see what happens. Let's talk about probability questions. Now, a lot of people find probability questions to be hard, but I think it's because they don't know this hack that I know. Okay, it's just a framework that I follow. Okay, it's very plug and play. Probability questions are very easy to me, and I'll show you how I solve them. Okay, all you have to remember is target over total. That's it. You can think of it as a formula. Okay, target over total. What do I mean by target over total? Okay, so let's say we're trying to draw the hearts from a deck of cards, and we have to calculate the probability that the card we draw is hearts. Okay, like the face of the card is hearts. Okay, so what is the total? Okay, the total is how many cards. Let's say it's a full deck of cards, 52 cards. Okay, if you search up how many cards are in a deck of cards, it's 52. I hope it's 52. Okay, so 52 cards in total. So that's our total. That's where we're drawing from. Okay, and then what are we drawing for? Like, what's our target? That's hearts. Okay, there's 13 hearts. Okay, there's 13 of each face in a deck of cards. So there's 13 hearts. That's a target. That's what we're trying to draw. There's hearts. There's 13 hearts, and out of what we're drawing is 52. So that's the formula. Okay, it seems pretty easy, but it gives you a framework. So you always look for the total first. Okay, you always find what is the total. What are we drawing from? And then you look at what are we drawing for? Okay, what's the target? And then you just put target over total. Now, something that's pretty important is the target has to be from inside the total. We can't say 14. We can't just magically count a heart from another deck of cards when we're only drawing from this deck of cards. Yeah, that might sound obvious, but I'll show you what I mean, like why that's really important. Okay, so let's use that framework. Okay, remember, target over total. And we look for the total first, and then once we have the total, we look inside the total to find what the target is. Okay, so let's look at this very standard probability question. Probability questions usually have tables, but if you see a table, it's pretty much guaranteed a probability question, or like how you solve it is exactly how you treat probability questions. Just look for target over total. Probability questions, honestly, you probably don't even need to read the entire thing. I will read it just because I have tons of time in the math section. Like I can finish the test with 14 minutes left and still get an 800. So there's no point in me not reading the entire thing. But if for some reason you're in module 2, you probably don't need to read the entire thing. Like you just need to read the last sentence because it's pretty much the exact same. Like it's literally plug and play. I swear the SAT, they just take the exact same question and then change the numbers a bit. Maybe make it 2 columns instead of 3 columns for a table. And then that's it. That's all they change. It's literally the exact same question over and over again. That's why probability questions are so easy. But in summary, we have to look for the total, right? Look for the total first. So we just jump immediately to the last sentence, honestly. The rest of the sentence is just telling you like what this table is about. And you can pretty much guess what it is about. Okay, if a person is chosen at random from those who record at least one dream. So right away, it gives us our total. It says like where are we choosing from? Okay, like what are we drawing from? That's our total. So it says from those who recall at least one dream. So I'm assuming 1 to 4, 5. That's how many dreams. It really says dreams recalled during 1 week. So we probably need to read the entire thing to get the context of it. That's what I mean. Okay, it's pretty much the exact same thing. They might switch the x-axis, like they switch the title of the graph about something else. But it's pretty much the exact same question every single time. So first, find the total. It's going to tell you the total. I promise it's going to tell you total. It might say given this, or given that those who recall at least one dream. If it says given choosing from, something to do with that's the total. Okay, you should be able to just understand it and you just tell what the total is. But always start with the total. So the total is at least one dream. So I'm assuming this is dreams. Yeah, this is dreams recalled, right? So 1 to 4. So that includes this part. Also this part, because if it's 5 or more dreams, that's still more than 1, right? We're looking at least 1 dream. So the total is this, like all of these. So we're gonna add all these up. Okay. It's really just, if you look at this 39 into the total of these two. This 125 total. So you really just add these two, or you can just add up all 40 of these numbers. It doesn't matter. Okay, so let's just do it the normal way. 28 plus 11 is 57 plus 68. 164. Okay, so that's the total. Remember, we need a fraction, right? We found the total. So now let's find the target. Okay, what is the target? What are we drawing for? What is the probability? It's probably going to be, it's going to probably tell us what the target is. What is the probability that the person belongs to group Y? Now, I have a question. Is this the target? The answer is no. That is not the target. This is the target. Okay, you cannot include the 21 inside the target. Okay, remember, the target has to be inside the total, okay? The total was these 4 numbers. You can't make the target than this. Like, this is outside of the total, okay? It's impossible to draw things that you're not even drawing for, okay? This is where we're drawing from. You can't draw this. So, obviously, you can't include the 21. So, people get confused. They see, oh, belong to group Y. They immediately think all of group Y is the target. No, it's just the part inside the total. So, it's only 11 plus 68, which is 79, right? Mental math. Okay. I put 79. So that's literally it. Target over total, right? 79 over 164. And wow, the answer is C, right? You can also simplify this. That is simplified. But like if for some reason you don't see the fraction that you have as an answer choice, just press this button. It's going to simplify the fraction for you. And then that's probably going to be the answer. So hopefully it's very straightforward. Again, always look for the total first. And look for the target, make sure the target is inside the total. It's just that formula over and over again. Now, there are some harder probability questions, which I'll show you. Okay, this is a pretty rare. I've actually only seen 1 probability question ever at like this type of probability question. But this is like pretty much the hardest probability questions can get, in my opinion. Like I've never seen one harder than this. And to be honest, this one isn't even too bad. So pause the video, see if you can solve this. Okay, use the exact same formula. Okay, target over total, but look for the total first. Like what are we drawing from? What's given? Okay, and then find what you're drawing for, and then do that. Okay, pause the video. Hopefully you try solving it. Let's read this. So it says a library has 3 shelves dedicated to mystery novels and 4 shelves dedicated. Okay, this library. Oh, it's a library. Yeah, it's expected that they have that many novels. Each shelf of mystery novels contains 10 hardcover books, 5 paperbacks. Okay, so I see. So it's like this section of shelves has 2 types of books, and this section of shelves has those same 2 types of books. Okay, a book is selected at random from one of these shelves. Okay, so when I'm reading the last sentence again, the last sentence is super important. Well, I read this because I kind of need to know what the context was. If there's a table here, I usually, I still read it just because why not? But usually you just read the last sentence right away, and you can just find what the total is, like we did before. Right? I pretty much just skipped this entire part. Let's look for the total. So a book is at random selected from one of these. Okay, that doesn't tell us much. It's just like a book is selected. What's the probability of selecting a novel? Given, okay, this is important. Given that the book is a hardcover, and I think if you practice this, you'll realize like it's a really good skill to be able to figure out what's the total. Like, given that the book is a hardcover, that's our total. Like, given, where are we drawing from? Like, what's the total? Okay, where are we drawing from? Given, so it's a fact that the book is a hardcover. So that's what we're drawing from. Only out of the books that are hardcover, that's what we're drawing from. We're drawing, and that's the target. It's like in sci-fi novel. Okay, so first, let's find how many hardcover books there are. We need to calculate this because we need to find the total, right? Okay, this is the hardest probability question you can get. So if that gave you trouble, which I think it's pretty simple, but if that gave you trouble, then it's okay. As long as you understand this, you'll be fine. Like, I promise you'll be fine. This is the hardest probability questions I've seen. This is literally the hardest. Okay, 3 shelves dedicated mystery novels and 4. Okay, and then so there's 3 shelves, and inside dedicated mystery novels, and these mystery novels contain 10 hardcover books, or each shelf. Okay, I see. So there's 3 shelves, each shelf. So that means there's 30, right? In the mystery novels, there's 30 hardcover books because there's 3 shelves and each shelf has 10. So 3 times 10 equals 30. Okay. But that's only the hardcover books in the mystery novels. What about the hardcover books in the sci-fi novel? Let's look at that. So there's 4 shelves of the sci-fi novels, and each shelf has 6 hardcover books. Okay, so 4 times 6, 24. Okay, so we know out of all of the 7 shelves, right, the 3 mystery novels and the 4 sci-fi novels, there are 54. 30 plus 24, so 54 hardcover books. That's our total. That's what we're drawing from. Okay. What are we drawing for? What's the target? Right. So we know the denominator is 54. What is the numerator? That is probability of selecting sci-fi novels. So only sci-fi novels. Okay. So again, you can't do 6 and you can't do hardcover and paperback. It's only the hardcover because in that side of our total, it's only hardcover books. So when it says each shelf of sci-fi novels contains 6 hardcover books and 4 paperback books, we can pretty much ignore the paperback books. Paperback books is not inside our total. Right. So it's the 6 hardcover books, and obviously there's 4 shelves of 6 hardcover books. So the total amount of sci-fi novels inside our total is just 4 times 6, 24. Okay, and you see 24 over 54 isn't one of our answers, but we can press this. It's going to simplify the fraction for us. 4/9, which is an answer choice A. That's the answer. Hopefully that made sense. And again, if that didn't make sense, I would rewatch it and just make sure, like, whatever part doesn't make sense, just pause it there and try to process it until you understand it. Then keep on watching it, because I would make sure you understand this. If you can understand how to solve this question, you'll be set for probability questions. There's pretty much nothing else that they can throw at you. Okay, now I'll go to a slightly rarer type of probability question that I would like you to know, but it's still the same formula. Target over total. Okay, so see if you can figure this out. Okay, this would be a fun IQ puzzle. I don't know. See if you can figure it out. So pause the video. Try solving this. Okay, hopefully you paused it. Let's read this. Okay, because this is actually. Do I need to read it? Probably not, but I'll read it. Human blood can be classified into 4 types. Presence. Okay, yeah. I basically didn't need to read this at all. Table above shows distribution. But yeah. Okay, it's just random stuff. Okay, the last sentence is what's important. If one of these people who is negative, so yeah, you can pretty much like you don't have to read this at all to know what it's referring to. So these people who is negative. So this row is chosen at random. So that's right away. That's our total. It literally says if these people are chosen at random. So that's what we're drawing from, right? So that's our total. We can probably write that right away. So it's a fraction, right? Target over total. The total is all these added up. 7 plus 2 plus 1 plus x probably, right? 7 plus 2 plus 1 plus x. That's our total. Okay, and then x is just like what we don't know, right? Yeah, like we just don't know what x is. So that's what's changed. Like this type of question is different from the previous 2 questions we get. The previous 2 questions, we were trying to find the probability. I think this question, it tells us the probability. Yeah, it literally tells us the probability, and we need to find a number in the table instead. But we use the same formula. Okay, I'll show you. So it's chosen at random. The probability, so that seems to be our target, that the person has blood type B. So blood type B is our target. Blood type B. Right, so it's not 9 plus 2, it's just 2, because inside our total was just the bottom row, right? So it's only the 2 which is in the bottom row that counts. So our target is 2, but it tells us what this equals. It tells us that this equals 1 over 1/9, right? And we just need to find x. So there we go. We can really solve for this because this is a single variable equation, right? It's one equation. I put a squiggly line because I'm already prepped of what to do. But yeah, here's our equation. And I can solve for x just by turning it into regression. If you haven't watched my Desmos stuff, I would highly recommend you watch my Desmos stuff because you can just solve questions like this. It's ridiculous. Okay, so x is equals 8. X equals 8. And then that's pretty much it. Yeah. To target over total. And there's not much to it. You see, we used the exact same formula to solve this. But in this case, we were given this and we just had to find one of the numbers in here. But it was the exact same process either way. Just use the formula and then just type in the stuff that you do know. And you can just have Desmos solve it for you at the end. And that's literally it for probability. Just remember, target over total. Look for the total first. It's usually what is given or what is chosen at random, or basically what you're drawing from. It's going to be in the last sentence. Just understand the last sentence and find that total. And then just look for the target. Like, what are we selecting? Okay, just pick that and make sure that that's inside the total and just do target over total. That's going to be our answer. Let's go over how to solve generalization problems on the SAT. And generalization problems are just basically any time the question mentions samples, right? You see sampling method samples. This question, scroll down. This question mentions surveys of random samples. So any type of question that mentions samples, that's going to be a generalization problem. So first of all, let's try to understand like the why we're taking a sample. So let's say we're trying to estimate who's going to win the election in the US, Donald Trump or Joe Biden, okay? And we're trying to predict it. We're trying to predict who's going to win. This is before the election actually happens. How would you do it? How would you do it? You would take a poll, right? You would just like get some people, because you can't survey everyone in America who's going to vote and go like, who are you going to vote for? Like that would cost way too much money. It's probably not feasible because people like wouldn't want to respond. So what do you do instead? You make it easier for yourself and instead just get maybe a few thousand people, maybe like 2,000 people. Instead of trying to survey, 300 million people, to survey 2,000 people and get what those people are going to vote for. Like get the statistic from that. And let's say only like 55% of the people in the 2,000 are going to vote for Donald Trump. And you could be like, okay, then probably guess that all of America will also vote for Donald Trump. Like 55% of people of all America can vote for Donald Trump. That's the logic of sampling. Basically, it's feasible or like too expensive or something like that. It's just not possible to get the actual number, right? We're trying to get who's actually going to win. Like what percent of people is going to vote for Donald Trump? We're trying to predict that. We can't actually do that. We're just going to estimate it by a sample, like taking a poll, right? Getting a small amount of people, then seeing how much of those people vote, and then using that to then generalize or to make an assumption that, everyone in America probably vote for that. Now, there's obviously problems with this, right? You can't just take 2,000 people from Texas. That would be a horrible idea because Texas is a Republican state. It's a very strong Republican state. There's a really good chance that if you only take people from Texas, they'll tend to vote for the Republican side. Like they'll vote for Donald Trump more, right? Let's say you live in California and you want to make it really easy for yourself, so you're only going to take 2,000 people from California. That won't be a good idea because California is a very strong Democratic state. They'll probably vote for Joe Biden most of the time. Like most of the people there will vote for Joe Biden. So your sample will be very biased. Instead, you want your sample to be a representative representative to what's actually going to happen in all of America. So how would you do this? You would pretty much get a list of everyone in America and just like randomly pull 2,000 people. You want to do randomized because it takes care of the biases, right? Because like if you accidentally only take people from Texas, then it's going to be Republican. If you do random though, it's going to basically negate all of that. So the random chance will cover everything, and it would just be pretty close to the actual population. So let's give you an example, like to explain this example. So let's say out of the 2,000 people, only 1,100 people voted for Donald Trump. Well, it said that they were going to vote for Donald Trump. Okay, that's about 55% of that sample is going to vote for Donald Trump. Then you could say, okay, because and imagine you took a random sample from all of America, and this was like a pretty good representative of like all of America as well. So since you got 55% of the people from here voting for Donald Trump, you can then say, then probably the 300. Wait, how many zeros? Wait, this is 30 million. So 300 million. Okay, it's probably less than this, but let's say 300 million people are going to vote. Because our sample, we found 55% people voted for Donald Trump, we could then predict that 55% of the 300 million of everyone going to vote is going to probably vote for Donald Trump too. And then, so that's going to be how many people are going to vote for Donald Trump. Okay, that's our prediction. So that's what we're getting at. So try this question. And these questions have more to do with like conditions to make sure you can generalize correctly. But try this question. See if you can solve this. Pause the video. Okay, hopefully you had a chance to solve this. I'm gonna go over this. To determine the mean number chosen per household in a community, Tabitha surveyed 20 families in the playground. So that's a problem. Just like how we were trying to predict who's gonna win, or how many people are gonna vote, or like what percentage of people are gonna vote Donald Trump in the election, they were trying to determine how many children per family on average is in the entire community. But they're only surveying 20 families in a playground. Why would a family be in the playground? Why would somebody be in the playground? Probably because they have children, right? So this would be extremely biased. This is like asking, like only taking 2,000 people from Texas, right? It's kind of biased because people at a playground probably have children. And if you're trying to estimate everyone in the entire community, how many children they have, you're probably going to overestimate it if you only take people from playground, because those people tend to have more children, right? Because they're in the playground. That means this is biased. You notice it didn't say the word random. For samples to happen, they have to say the word random. The sample has to be taken randomly from the population. In this case, it's not. They actually only survey people from the playground. So that's definitely something to do with bias. Yeah, so D. Wait, no, C. Right? The sampling method is flawed and may produce a biased estimate of the mean number of children. Yeah, that's C. So again, if it's not random, then it's going to be a biased sample. Just remember that. And hopefully you understand the logic behind it too. So that way, if they throw like a trick question at you, you'll still be able to understand it. Okay. Let's do another thing. Try solving this question. Pause the video and try it. Okay. Hopefully you solved it. Let's do this. A sample of 40 fourth grade students was selected. So it was random. That's good. Selected at random from a certain school. Okay. The 40 students completed a survey and 32 sides. Okay. Yeah. Blah, blah, blah. Which of the following is the largest population to which the results of the survey can be applied? So anytime it says largest population, or just like which population can we generalize it to, something like that, it's always going to be the population you took the sample from. Like, where did they pull the sample from? Like, as in, like, we did a sample, we took 2,000 people randomly from the US, right? And all of the US. But if we only took 2,000 people from, let's say, New York, then we could only say New York is probably 55% of people in New York can vote for it, are going to vote for Donald Trump, not all of America, right? Because if we only took the sample from New York, and 55% of people from that sample voted for Donald Trump, we can't say the same thing for all of America, because New York is probably not the same. Like, the people who live in New York are going to be different, at least not close to all of America, right? All of America, like, there's different types of people in all of America, and New York only has this, like, a select type of, and there's probably a bias in New York as well. So same thing here, right? We're taking the sample from a certain school, and we're only taking fourth grade students. So all the in our sample is only fourth grade students taken from a certain school. So that's all we can say. Like, this estimate of the 32 out of 40 people, we can only say that applies to the fourth grade students at a certain school, at that school. Right? We can't say all fourth grade students in the world. Like, that doesn't make any sense. Only from this school, right? Maybe this school is like Catholic, right? They probably have a different opinion than like a public school. Things like that. Okay, let's move on. The 40 students who were surveyed, this, you could generalize to that, but like, it's asking for the largest population. So it's always going to be the population we took the sample from. I mean, you could say, oh, like 32 out of 40 people are going to, so we already know that. It's not like, it's pointless to do, 40 students who were surveyed. Like, what's the point? You're doing the 40 students to actually predict all 40 students in a certain school, what they're going to do. Right? That's the entire purpose of you taking the sample. And that doesn't make sense. Just remember the large population is just where we're taking the population from. Okay. All fourth grade students at the school. Yeah, that's exactly what we said. Like, fourth grade students from the school. All students at the school. No, because there could be like third grade students, but we didn't take, like, the sample wasn't taken from third grade students. So we don't know. Third grade students might have different opinions than fourth grade students. We can't just say because these fourth grade students did this, we say the third grade students did that as well. That doesn't make sense. Okay. All fourth grade students in the county. No. It has to be in the school. This is all, like, there's multiple schools in that county. We don't know. We can only take it from that school, because we don't know if this school is different from the other schools or not. Okay. Yeah, so the answer was B. Hopefully it makes sense. So that was conditions to generalize. Okay? It's just only two things, you notice. You have to remember. It has to be a random sample, and the population you generalize to, the largest population you can generalize to, is where you took the sample from. That's the population you can generalize to. Let's move on to, like, actual generalization problems. I think those were two, but this is like you actually doing the calculation. Try solving this question. Pause the video. Okay, hopefully you had the chance. Let's go over this. This is the exact same thing, right? As we're voting for the election. 3 out of 200. So basically what's happening here is there's 10,000 cars, right? And they're trying to predict how many of these cars will have a defect, or will not be fit to sell, I guess, because there's a defect. But they can't say 2,000 cars and then say, oh, how many cars have a defect, and then they're wasting a lot of money. They're trying to decide if they should actually produce the cars in the first place or not. But they're trying to based off of the defect rate. Right? Maybe it'd be too expensive and too many cars have defects, so that way it's too costly to actually manufacture these cars. So instead, they're just doing 200 cars. I just say 200 cars and then see how many of those have, and then we could say, okay, this is an acceptable amount of cars that usually have a defect, so we can probably produce all 10,000 of these. Things like that. If that doesn't make sense, just remember it's usually the smaller numbers, right? The sample is going to be smaller than the population. So just take the two smallest numbers and you divide them. That's going to be the percentage. I'm really, really generalizing this. So I'm just okay, the two smallest numbers, you just divide them and then you multiply it to the big number or the population. But hopefully I want you to understand why you're doing this though. Don't just remember, two smallest numbers and then multiply to the bigger number, or get the percentage and multiply to the bigger number. I want you to understand why you're doing that, because I feel like SAT do throw in questions where they ask you you have to know the theory behind why you're doing it to be able to answer the question. But hopefully this makes sense. We take the sample. This is the 3 out of 200 is the rate that they're having a defect, and then they're okay, so assuming all the 200 cars is similar to all these 10,000, we can then just go let's multiply that percentage to 10,000 to see how many cars will probably have a defect rate, because they're assuming 10,000 is close to this defect rate. Hopefully that makes sense. Okay, so yeah, the answer is A, 150. Now let's talk about margin of error. So back to the election thing. Let's say your job was to report to your boss and say what percentage of people are gonna vote for Donald Trump. That's your job, and you got 55% from the sample. Would you say 55% to your boss? What if your entire salary was based off of this accuracy of this number? But you wouldn't say 55%, because it's probably not 55%. This is just the estimate. We can't be 100% sure it's 55%, right? Because all we did was just take 2,000 people from all of America, randomized, and did. It's a pretty good sample, but we don't know for sure. The only way we can actually know for sure is if we time travel to the future, saw the election, and then report it to the boss, right? There's no other way to know for absolute sure. This is just a guess. So you wouldn't say 55% to your boss. Instead, you would probably say there's some percent chance, it's really likely that it's gonna be between 50 to 60%, right? It's probably 50 to 60%. We don't know 55%, and we're just giving some wiggle room, right? The actual number is probably between 50 or 60%, and things like that. So there's a bit of uncertainty. We're not sure, but we know it's close to 55%, right? Because that's the hypothesis are doing it. So it's kind of close to 55%, but we don't know. And 55% is going to be the exact number. So let's give it some wiggle room. Let's give it a range 50 to 60. And this is margin of error. The bigger this range, the higher the margin of error, by the way. So margin of error is actually the measure of how uncertain you are that this is actually correct. 35% is correct. And what is the margin of error here? The margin of error here is actually 5%, right? Because the margin of error is just plus or minus the statistic. So we had 55% here. So margin of error is 5. Because if you do 55 minus 5, it's 50, and 55 plus 5, it's 60. So again, margin of error is just plus or minus the statistic you calculated, and it produces a range. And basically, margin of error is just the plausible range that the actual statistic is in. Because again, we don't know for sure. It's not going to be 55%, probably not. But we know it's close there, so we just give it a range, and then we can estimate based on that. So try solving question 10 using what I just said. See if you can do it. Okay, hopefully you solved it. So we're trying to estimate margin of error, and we see the statistic is 23%, and margin of error is 4. So 23% is the same thing as 55% here, and 4 is the same thing as the 5% here, right? So what is this? This means 23 minus 4 and 23 plus 4. That's the range. 23 minus 4 is 19, 23 plus 4 is 27. So it's the plausible range between, it's basically saying it's plausible that this statistic, I don't know what the statistic is, they're trying to estimate 23% of the students in the population saw a movie. Okay, so saw a movie at least once per month. So the margin of error, with the margin of error, you would estimate that between 19 and 27% of the students in this large university saw a movie at least once per month. Yeah, that's the range. So the answer would be D then. And you see, it's pretty easy. You just get the range, and it's like either C or D, and it's obviously D, because this is actually the plausible range. No, 19 is not the certainty, right? This is the research between sure and 19 to 27% sure. No, it's not that. It's the plausible range, the actual statistic. It's not like how confident you are that it's that most it doesn't even make any sense. Like most students, no, like it's actually less than most students, right? So like this definitely doesn't make sense. It's definitely not your confidence. Confidence levels are a separate thing, which I've never seen them test on the SAT actually. So I wouldn't worry about confidence level. But it's the plausible range. Remember, margin of error is the plausible range of the statistic you're trying to estimate. Okay. Let's move on. Just one last thing. Let's talk about margin of error more. But what actually determines the margin of error? Like how can you tell if what you got is pretty close to the actual thing, or like you're not that certain of that estimate? How can you tell? Let's say you're trying to estimate the probability of you flipping a coin and it landing on heads. Okay, let's say you actually didn't know, because we obviously know there's a 50% chance probably that if you flip a coin, it's gonna land on heads. But let's say we didn't know that. We didn't know that there's 55% chance of landing on head. How would you estimate it? You probably just flip a bunch of coins and just like calculate it and then see, okay, it's probably 50% because like half the time it lands on heads, right? That you do. But if you just flip 20 coins, do you think that would be a good estimate? Let's say you flip 20 coins. Would you be surprised if it got 15 heads and 5 tails? Probably not, right? Because like that's a pretty expected thing to happen. 15 times out of 20 it lands on heads. That's not as surprising. So then if you only flipped it 20 times, it'd be like, oh, there's a what is 15 divided by 20? 75, right? Yeah, so there's a 75% chance it lands on heads. We know that's not true. It's just because you flipped it too little times. We need to flip it a lot more so that we have more data over time so we actually like see the actual statistic. Let's instead say, instead of 20 times, we flipped it 20 million times. Okay, we flipped that coin, we just sat there for decades, and we flipped it 20 million times, and we tracked every single time if it landed on heads or tails. What would you expect to happen? You'd probably expect there to be like 50.0000001% of the time it lands on heads, and 49.99999% of the time it lands on tails. Right, that's a pretty, because we just flipped it so many times that there's just so much data that it's probably going to be really accurate. If that makes sense. Like the more data you have, the more certain you are that you got the actual statistic. So that's what it means. Okay. What do you think happens if you have a higher sample size? A higher sample size just means like you have more data, right? Because the bigger the sample, the more data. So instead of surveying 2,000 people in America, you surveyed 100,000 people in America. Like that's a difference in sample size, right? So if you have more data, if you collect more data, like more people, like more trials, just more data overall, what happens to margin of error? Remember, margin of error is a measure of uncertainty, right? What happened here with the uncertainty? We got more certain, right? You'll probably be more confident in an estimation if you did it 20 million times versus if you only did it 20 times, right? More data means you're more certain, right? You reduce the uncertainty. So that means when sample size increases, margin of error decreases. Because this is saying as you get more data, your uncertainty decreases. You're more confident in you. So margin of error decreases. Hope that makes sense. So remember, sample size increasing, margin of error decreasing. And hopefully like my explanation made sense to you and you know why as well. Because the SAT, they might test you on different theories. But really just remember, margin of error, it goes down when sample size increases and vice versa, right? When sample size decreases, margin of error goes up. Because as you have less data, you're more uncertain. Okay, try solving this question now. See if you can do it. Okay, hopefully you solved it. And you got it right. So what is this saying? It's saying, what is the appropriate reason the margin of error for sample A is greater than the margin of error for sample B? So why is the margin of error for A bigger? Remember, sample size, it has to do with sample size, right? This means sample A, they're more uncertain about sample A because the margin of error is bigger. There's like a bigger range that they're going to say, like the statistic falls under. So they're more uncertain. That probably means the sample size is less because they have less data, so they're not as certain. And these guys, this sample probably has more data, so they're more certain about the statistic. So we're looking for sample A having less data, or a smaller sample size. That means less data because they have less data points, right? Less things to, what is the sample for? I don't know, but you get the idea. Sample selected population, and samples of votes for proposition. Okay, yeah, so they have less votes of propositions, so they don't have as much data. Okay, answer is D, right? Sample size is lower when there's higher margin of error because there's more uncertainty. So the answer is D for that. One more thing, I'm not sure if this will show up on the test that you'll see, but it might show up. There's a chance it shows up. It only showed up one time. I think it was in the November 2024 test. And it might have just been like a trial question they did, this experimental question, but I'm not sure. And it might show up again. So just in case it shows up again, I want to make sure you can solve this. Okay, try solving this question actually. It's like just pull you in the deep end. See if you can solve this one. See if you can do it. It's kind of the same logic behind like you haven't. I won't spoil it. So try solving this actually. And pause the video. Okay, hopefully you solved it by now. So this question asks us what is necessary to establish a cause and effect relationship between two variables. Anytime you want to establish a cause and effect relationship, you have to make sure it's randomly assigned. And that's all you have to know. Make sure like it's randomly assigned between the two groups, because I'm assuming there's two groups in here. You have the treatment group and a control group, right? You have to make sure that it was randomly assigned between the two groups. That's what I look for. So cause and effect equals randomly assigned. It's the same logic behind you having to, like, the sample has to be random, right? Or else it would be biased. Right? It's the same logic. You want to make sure it's not biased at all. And you can actually do a cause and effect relationship. You have to make sure it's randomly assigned between the treatment and control groups, or the two groups that it mentions. So the answer here is actually B. And that's it. It's cause and effect equals randomly assigned. And that's all you have to remember. And in case it shows up, I'm not sure. It probably won't, honestly. But in case it does, I want to make sure you know it, that you can do this, because I've never seen this question. I've only seen this question once. I feel like it was an experimental question, but just in case it does show up, now you know. Okay, that's all generalization. It's mostly just sample stuff though, and you just have to remember, just understand like the example I gave you with trying to predict the election outcome, and I think you'll be fine with this. Just make sure you understand everything, and understanding is better than just like rote memorization. So hopefully understanding this will help you memorize it. So like help you to make sure you understand everything. That's my best bet. And if you can't wrap your head around it, just remember the sample for conditions to generalize it, to make sure you can actually do the generalization. You need it to be a random sample, and you can only generalize to the largest population. You can only generalize to the population you took the sample from. That's the largest population you can generalize to. And also, you just divide the two smallest numbers, like the smallest number over the second smallest number times the biggest number. That's probably going to be what the answer. Or if it gives you a percent, I just multiply the percent to 10,000. Something like that. Okay, it's like the estimate to the population. And also margin of error, it's the range, the plus or minus that. I think that's pretty easy to remember. And also higher sample size equals lower margin of error. Okay, and that's it. You've made it to the end of the video. I want to, first of all, give you a huge congratulations with the confetti button. There it is. I want to give you a huge congratulations because you have learned all of problem solving and data analysis. Technically, if there's a single question on the SAT that appears that has something to do with statistics, you now know how to solve it. However, there is a difference between knowing how to do something and actually being able to do it. So while everything is still fresh, while you still know everything, and if you don't fully know everything, if something didn't fully click, I would rewatch that portion and slow it down maybe until you fully understand it. Once you do understand everything though, I would go to the question bank, go on one prep, select problem solving data analysis, select all the hard questions, and just grind it out. Make problem solving and data analysis questions one of your strengths when you're taking the test. I'll see you in the next video.